Okay. So a bit about myself. I am the senior scientist at the Tampa Bay Estuary Program. Been in that role for about 5 years now, and I oversee a lot of the science the program conducts. But as you probably realize, I have a huge interest in data science and developing open source tools. So that involves a lot of the work I do at the Estuary Program, but also some external work I do with partners like Jill. And I basically do a lot of stuff in R, building a lot of R packages that are meant to support the environmental sciences and management decisions around coastal management. And so that's where EBASE comes in. Um, I would ask Jill to introduce herself, but she's in a very, very loud Starbucks coffee shop right now. So she will be in the chat entertaining questions or any issues you have related to the workshop. We do have a lot to go over today, so I'm just going to jump right into it. I was thinking about doing introductions for everybody, but I think I'll forgo that. Um, I think you all have seen the course website. All the content is on here. I'll be going through the modules today. Hopefully everyone has done the setup for the workshop. If not, God help you. But we're going to do a mix of going through the content and mostly live coding and exercises as we go. I've linked to the package web page for EBASE. There's a nice package down website here that gives you probably way more information that you'll ever need for this package. But essentially, we're going to go through really the vignettes for this R package and do a little more hands-on training that hopefully is a little more accessible than what you might find on the website. But if you have any information or any questions about the information related to EBASE, check out the webpage. Also, of course, this is based on some research that was recently published that really goes into a lot more detail about why we developed the package and some of the decisions that were made in producing it. So our agenda, let's see. So by 10:30, hopefully I will have gone through an introduction of what metabolism is all about. And then 10:30 to 11:30, we talk about how do you prepare data for use with EBASE, and that is largely focused on swamp data. But as I mentioned, any continuous monitoring data can work with this package. Then we'll have a short break. So definitely encourage you to get some lunch, drink some coffee, go outside, scream at the sky, whatever you need to do. Then we'll come back at 12 and we'll get into the bulk of what EBASE really does. And I did leave some buffer time, as I said, related to just discussion or if we run over time, which spoiler, we probably will. But I do have some time at the end where we can just have a free form chat of how do you want to use this stuff? You know, what's useful for you? We could do some scenarios of how you might run some analyses using some real world examples, whatever you want. But I'm hoping we won't go all the way to 3. So hopefully we'll get out of here a little early. Important links, y'all are in the chat or the call now, so don't need to go over that. We have a live coding link right here. I will put that into the chat. Basically, this is a file that is synced on my computer that if I remember to save it constantly, you should be able to access that same live coding link and copy and paste my code that I'm going through in real time. This is synced through Dropbox. You don't need to log in, but you should be able to see it. So if I do 1+1, save it, and go to here and refresh it, maybe in theory, is my Dropbox on? Let's see, waiting to sync. Well, in theory, it should work. Let me close Dropbox and start it again. Let's see, sync. It says it's syncing. Now it's thinking. Okay. Okay, so there it is. So basically, you should be able to use this as a backup. You know, I would like you to code along as I go through this on your own using RStudio. that you installed. But if you get lost, you can always just copy and paste the stuff that I'm doing from this live coding link. It's just sort of a backup. Um, is anyone here using Posit Cloud for this workshop? Speak up or type in the chat.
Yes, unfortunately, I am.
Okay. Did you get that set up? Okay.
Yep.
Okay, good. Again, that's just a backup. Ideally, you should have RStudio installed on your computer, but this is available if you cannot get it. Sounds like most folks are using it on their own. So those are the links. Really, the only ones you need to be aware of right now is the live coding link, as well as the training website, which I will put back in the chat there. Housekeeping rules. Yes, feel free to interrupt me at any time. I hope this is going to be more than just a one-way exchange of me talking to you the whole time. If you have questions or you're like, I don't understand anything that you're doing, unmute, ask me, feel free to speak up. Also type questions in the chat. Obviously, I won't be able to get to them as I'm going through the content, but hopefully Jill will be able to answer some of them. Also, your peers that are in the room with you, feel free to answer questions from others if you know the answer. Let's see, use RStudio, yep, live coding link, and the website has all of the content that we're going to be going through. I am recording this, assuming that's okay. I am hoping to put the content on the website once it's recorded after this training, probably sometime early next week. So it'll be available for you to review. Also, of course, for those that are unable to attend. And this website will stay online in perpetuity. It will be your resource. There's way more content on here than I anticipate going through today. So it's more of a living document that you can refer back to when this workshop is done. Code of conduct. This is pretty standard for any sort of group activity in the open source world. Basically, don't be an ass. If you're an ass, I'll kick you off the call. But you can read the details there. I think we're all pretty cool, so I don't anticipate that being an issue, but it's good to state that up front. And finally, as far as feedback goes, I will likely set up a survey to send out to y'all after the workshop, but more generally, EBASE is a tool that we've developed for you as potential users. So obviously we want it to be useful for you all. If there are ways you feel like it could be improved, definitely feel like you can reach out to myself or Jill with any of that feedback, or if you encounter any bugs or challenges using the software, we are here to help. If you're GitHub savvy, you can, of course, enter an issue on the main GitHub repository for it as the more standard way to suggest enhancements or fixes to the software. That's another option that I encourage. Okay. Any questions about any of that before we dive right in? Everybody's good to go? All right. Cool. So, all right, let's do the introduction. This is not going to be any coding except for the end. I essentially, with this lesson, it hopefully will be fairly quick, but I wanted to obviously just introduce some basic concepts about what ecosystem metabolism is, and what it tells you about your ecosystem. Also understanding the various ways it can be measured. There's several, and EBASE is just one of them, but some of the more standard ways of using continuous monitoring data really form the core of what EBASE tries to do. So essentially, I want you to just appreciate or understand the basics about it. I was first introduced to the concept of ecosystem metabolism when I was doing postdoc work almost 10 years ago now. And first, I didn't quite understand what it was and why it's useful. So I want to impress on you all how it can be of value as environmental scientists or decision makers to assess the state of an ecosystem. Okay. At the end of this lesson, we're going to do setup of RStudio to make sure that we're queued up for the rest of the workshop. And if you've gone through the setup instructions as I send out an email. You should be good to go. All right. So, what is ecosystem metabolism? Simply put, it is a measure of how quickly organic matter is consumed or produced in an aquatic environment. If you know nothing else at the end of the workshop, that is a definition that you should be able to recite. Uh, it's the rate at which organic matter is consumed or produced. That's it. It's particularly important in estuaries because they're transition zones. They receive a lot of inputs from their watershed, but they also export a lot of uh, exports to the ocean or the atmosphere. So they tend to be very productive systems, and understanding metabolism in these systems can tell you a lot about what's going on. Um, Another way to think about it too is, you might be able to ask the question of like, well, why can't I get this information from measures like chlorophyll or nitrogen? Well, you can sort of make assessments about how productive a system is from these surrogate measures, but these are basically state variables that are essentially just concentrations or snapshots of what is happening in the system at any given time. Ecosystem metabolism is similar, but it is a measure of a rate or a process that gives you insight into sort of functionality of the system. So that's why it's a little more useful, because it does give an expression of how quickly things are happening in the environment versus just here's a snapshot of chlorophyll. Now, as far as how it's calculated, really it is expressed simply as NEM, or net ecosystem metabolism. And as I said, metabolism is a measure of how quickly organic matter is consumed or produced. We can symbolize that as production, how quickly things are produced, minus respiration, how quickly things are consumed. So it's the balance between production and respiration. And the methods that we're going to go over today are basically estimating both of those processes and taking the difference of them to get at what metabolism is. Okay, other concepts that are important to know is that basically if production exceeds respiration, so it's producing more organic matter than it's consuming, the system is basically said to be autotrophic. It's just churning out a lot of organic matter quicker than it's decomposing or being consumed. The flip side of that is you have a heterotrophic system where organic matter is being consumed more quickly than it is being produced. So those are other two key terms to understand: autotrophy and heterotrophy. We get that from NEM if it's positive or negative, based simply on the difference of production between production and respiration. Now, there's a lot of different reasons why a system can be autotrophic or heterotrophic, and it can vary a lot over time depending on what's happening in the system. And hopefully, some of the tools I'm going to give you today will help you assess things that are driving autotrophy or heterotrophy. Um, just to give you a sense of how metabolism varies between systems. This is from a really interesting paper that was more or less a synthesis of metabolic rates in different types of aquatic environments. Okay, so we see here's gross production in respiration. So production would be on the positive, producing organic matter; respiration being the negative, consuming organic matter. Notice also it's shown as a rate here. So grams of oxygen per square meter per day. So this is how quickly oxygen is being consumed or produced. And then we have also the four, basic designations of aquatic environments down here: stream, wetlands and ponds, lakes and estuaries. Because we are, I think most of us, coastal scientists, I want to draw your attention to the estuary. So because these are areas of transition, they receive a lot of input, produce a lot of input, and export a lot of organic matter. So we see a much wider range of production and respiration in estuaries compared to other systems. The other thing to note too is here we have basically, this is, you can think of the right side of this as just metabolism as a whole. So the balance between production and respiration. Most systems tend to be heterotrophic over time, just because they basically consume more than they're producing. overall. Again, that can change a lot from depending on time period and what's driving the system. Uh, but also think about it from the perspective of like streams, for example. So like these are generally more heterotrophic than other environments, okay? And that makes a lot of sense because streams are moving water. So physically they're exporting a lot and the running water systems tend to not be able to, there's not a lot of residence time there. So they're not, producing a lot to be measured at any given point in time. So intuitively, I think that makes a lot of sense. Um, Looking at estuaries in a little more detail, this is a paper by Jane Caffrey. I think many of you are familiar with her work, published about 20 years ago, that she did this broad scale synthesis of estimating metabolism across all of the nerve sites where there was data available at the time. And this was '04, so there was about 10 years of continuous data to do this. But she was looking at not only how metabolism varied across the estuaries and the nerves, but how they may have varied as a function of different habitat types. So again, this is getting at like what's driving metabolism. It's going to be the primary producers for the most part, things that are able to use inorganic nutrients to produce organic matter. So you have the reserves down here, and then you have the major habitat types here. Again, the same story is more or less that these habitats are going to be consuming more than they are producing. But if you look at something like SAV, so aquatic vegetation, these are primary producers. So they tend to be more or less balanced in terms of their metabolism compared to other environments that might not be considered, the primary producers. So intuitively, this makes sense. So again, I'm just trying to give you a sense of what might be driving metabolism to understand the importance of it as a measurement. Of course, nutrients are going to be driving that as well. There's a lot to say about eutrophy and oligotrophy and how that relates to metabolism. As you might expect, inorganic chemistry is a huge driver of system dynamics. And that is essentially what Jane Caffrey demonstrated as well. So this plot shows nitrogen loading, phosphorus loading, and how that affects ecosystem metabolism as it increases. And so you might expect this positive association. More nutrients means more production, outcompeting respiration. This is more or less true. As you can see from this graph here, most of these values are negative. So these are still heterotrophic systems, but as nutrient enrichment tends to occur, you get less heterotrophy, which makes sense because you're just getting more production, balancing out that respiration. But just because something has more nutrients doesn't mean it's going to be autotrophic all the time. Again, it varies a lot depending on when you look at it and just underlying conditions of the environment. Now, okay, this is just an example of like an event-driven change in metabolism. This is actually data from Tampa Bay in 2021. If you're familiar with what happened in that year in Tampa Bay, we had a huge release of wastewater from a fertilizer processing plant that basically introduced a lot of inorganic nutrients into the system. And you could see this is a couple months after, but we believe this stimulated a huge red tide bloom in the bay. And you could see it peaked around early July. So this is DO here. We started seeing a lot of Corynea brevis in the system at this point in time, a lot of fish kills, and that is reflected in the DO data as production sort of increased with Corynea, and then kind of sloughed off a couple of days later as the bloom kind of dissipated. So it's like that boom bust cycle of phytoplankton that can drive metabolism as well. Looking at it from actual metabolism estimates, this is from the same site where DO was measured. This is actually using a similar but distinct method from EBASE, just the basic ODM open water method, looking at production in green, respiration in blue, and then NEM in red. You can see basically you get, as DO increase, you get a spike in production in respiration because those two processes production, consumption, respiration are co-occurring. But also NEM kind of goes positive. So you get autotrophy at first, production outcompetes respiration, and then a drop, and then it bounces around a bit. But this is unpublished data, but it looks like essentially NEM is driven by that, whether it's autotrophic or heterotrophic, driven by that large bloom of cornea, and then it's senescence over the rest of the month. A couple other things to note about this. This is another method where you have these so-called anomalous estimates of metabolism, where you can get negative production and positive respiration. This is essentially a byproduct of the method itself, and these aren't real values. There's a lot to say about that, but it is one of the reasons why the basic Odom open water method, as it's calculated here, can be sometimes problematic. Okay, how is it measured? Well, we're coming up on 10:30, so I'm just going to blaze right through this. There are a lot of ways metabolism is measured. This is a list of some of them here, but most commonly is these open water techniques that rely on continuous monitoring data and essentially leverage a dissolved oxygen time series to sort of tease it apart and make different measurements about production and respiration. A couple assumptions from that approach, and so the EBASE approach uses Odom open water techniques basically, but this is the basic idea where if you measure oxygen in the water column, anytime you measure it at any point in time, it's going to be a reflection of how much productivity is happening, how much respiration is happening, and any sort of gas exchange you might have at the air-sea interface, okay? So not only do you infer or do you have to estimate these two parameters, you also have to include gas exchange. And there's a lot of different thoughts around how that can be accurately measured, and I'll talk a little bit later about how EBASE does that. It also assumes that the water column is well mixed, so you have basically no stratification from the top to bottom. What the sensor measures at any point in time is going to be a reflection of that metabolic history at that location. And things like tidal advection can really screw it up. We don't talk about that in this workshop, but this has been a point of frustration for coastal ecologists for a long time in terms of what the DO sonde is actually measuring. Is it that particular point or something, way far away that's just been sort of pushed to that sensor by advection alone? So we often assume advection is not a confounding factor here, but it often is. And just consider that when you evaluate a DO time series as a potential issue. So as I said, this is basically a breakdown of the processes here. You're leveraging the dissolved oxygen time series, looking at how DO changes per unit time, measuring production, subtracting it from respiration, and accounting for gas exchange. And then this factor here, Z, is going to be water column depth, which essentially converts everything to aerial units as opposed to volumetric. In that way, we can compare more easily between systems. And from this core equation, we can get NEM, all the other components of metabolism, and accounting for other things like gas exchange to more accurately infer what the processes are. Now, a bit about gas exchange. Like I said, there's a lot of ways to measure it, but most approaches basically follow this same formula where it's really a function of the concentration in the water column as well as the concentration at saturation and the difference between those two, because the more that gradient exists between the measured and the saturation potential, the more ingassing or outgassing you're going to have at the air-sea interface. There's also this parameter here, K, which is the gas exchange coefficient, which also accounts for other things like wind and how that can influence basically turbulence at the air-sea interface. As wind increases, you tend to see more air-sea gas exchange. Other factors like temperature can influence this, but this is the core model you get for gas exchange. And in its simplified form, it's pretty intuitive. The EBASE model uses a modification of this that looks scary, but it's the same principle. It's the difference between concentration, saturation concentration, and external factors like wind. So that's pretty much it. Um, that's your whirlwind tour of what metabolism is. Hopefully that wasn't too fast. Hopefully that made some sense. But before I move on to the interactive portion, are there any questions about any of that? I'm hoping most everybody is familiar with these basic concepts because I did go through that quickly. But yeah, if they're new to you, hopefully they made sense. Yeah, Harry.
Uh, Thank you, Marcus, for the overview. I just had a quick question about the ODA model. And like, if you account for other, like the lateral advection or like the benthic exchange, could you extend it to apply to like stratified systems?
In theory, like I said, in terms of the assumption about mixing, a lot of times we know that's not true. You know, you could have a salinity gradient or a thermal gradient. There are methods in another package that we created that can let you estimate it just on like say that top layer above the the pycnocline, thermocline, whatever. Um, I don't know if that's legit, but we we incorporated that in there. But really, these methods in general are meant to assess whole ecosystem metabolism. So it really is more appropriately used when the entire water column is mixed and you're getting all a measure of all processes that are contributing to DO change. Lateral advection, like the tide, like I said, that's a nuisance factor. There are detiding methods that we've developed that can account for that. It is a bit of trial and error, but we often do encourage exploration of those approaches if you do think tidal advection is a confounding factor. Basically, remove that effect to isolate a biological component in the DO to more accurately estimate metabolism.
Thank you.
All right. Okay, so now we're going to get ready for the workshop. Basically, you're just going to set up our studio if you don't have it open already. I strongly encourage, let me just move this over and I'm going to go over to my screen or my R Studio. So I strongly encourage you to use projects as sort of a modular approach to working in RStudio. It's much easier. You have the project home directory as your root directory there. You don't have to pull in external files from somewhere else on your computer. But basically, let me show you. So if you open RStudio, you can create a new project under the File menu, under New Project. Basically, you could make a new directory or put it in an existing directory. But if you haven't done this, I want you to make a new directory where you're going to use this for the workshop. Basically would, new project, find a place on your computer that you can access, and then create it. And then it'll just open up something that looks like this. Then once that's open, then open a new script. I'm not going to do that here because I have the live script that I'm using, but you would open new file, our script right here. Then I want you to basically save it, and this is going to be your working space for today. So hit the save button up here, give it a name. By default, this will be saved into the home directory of your project, so don't worry about putting it somewhere by hand, but that will be saved. And then essentially, I want you to set up the packages we're going to use today. So we're going to use EBASE, and I'm hoping everybody has these installed. We're going to use Swamp R. We're going to use the Tidyverse. We're going to use Plotly. We're going to use here. We're going to use do parallel. And actually, I think some of these, depending on time, we might not use them, but I want you to at least set up the loading functions. And actually, I'm going to go over to my live script. And once you have that, run the code. And you should get, a bunch of messages and stuff, but no errors. If you get no errors, you're good to go. You've got the packages installed, they've loaded correctly, and you should be set up. Now, the last thing I want you to do is create a data folder in your repository, okay? And this is where during the setup, I had you download a zipped file from the website. And this has all the data we're going to use today. If you haven't done that, it is right here put it in the chat right there. But basically create a new folder. So this has got a bunch of stuff for the workshop, but I have a data folder here. To create a data folder in your project, go right here, click new folder, name it data, and hit OK. And you'll get something like here in your file tree that says data folder. And then all you got to do is just drag and drop, or rather, I don't think you can drag and drop directly into RStudio, but you should be able to, let's see. If you go into File Explorer, you can do it from there like you would any sort of standard moving of files on your computer. But wherever you've downloaded the zip file, put it in this data folder for your project. And then you should be good to go for the rest of the workshop. I'm not hearing any feedback from the group, so I'm assuming everybody's got this set up. They've loaded the packages. They've got the data folder set up with the zipped file, and we're good. Speak now, or I will continue on with the lesson. Okay. I'm just going to operate under the assumption that everybody's ready. Okay, so let's move on to data prep. So that's lesson 1, Intro to Metabolism. This whole lesson, I'll try to do a hard stop at 11:30, so y'all can have a chance to get some food, take a break. But really all I want to do with this is to show you what are the data requirements for EBASE and how you would prepare data to meet those requirements to use the package. Because after lunch, we're going to dive right in and start using EBASE. If you load EBASE, there's a couple things that are available for you as an example file, as well as all the great documentation that comes with our packages. But that essentially shows you the format that is required for use with the package, okay? Generally speaking, though, most open water methods for metabolism require both water quality and weather data. Okay, and so like at the across the NERS, through the SWAMP program, all that information is collected. But the challenge is those things are typically collected by different monitoring equipment. So again, water quality is monitored by sondes in the water. Weather data is usually out of the water, well, out of the water always, and collected with thermometers and wind gauges and all that stuff. So you have to combine those two data sets before using EBASE. Now, the example data set that comes with EBASE, let me just show you what that looks like. So I've got EBASE loaded. If you're using RStudio, you can just type head example data or xstat. That's the file that comes with EBASE. And you could see what that looks like. So you've got 1, 2, 3, 4, 5, 6 columns. Let's just look at the size of that. So 27,000 plus rows, 6 columns. Essentially, it's continuous data. So each row is indexed by a date and time. And then you have dissolved oxygen, water temperature, salinity, PAR, and wind speed. So all of these come from the water quality sites. I guess depending on your setup, you might get PAR from a weather station, but wind speed definitely will always come from a weather station. So this is already combined for you. This is an example data set you can use with any of the examples in the package itself. It's just to show you what the data is supposed to look like. If you were to run structure on this, so str xdat, you can see the actual data types in terms of how R understands them. So this is a POSIX CT, which is, I forget what that stands for, but that just means basically a date time object that has a time zone attached to it. And all the rest of these things are numeric values. Now notice there's no units attached to these. We assume that all of these parameters are of the correct units. So what are the correct units? Well, I've got them right here, but if you ever want to know what the correct units are, you can look at the help file for this one. So if you did $exdat, you can see that in this help file right here. So DO, it's in milligrams per liter, water temperature, Celsius, salinity, PSU, PAR in watts per meter squared, which is tricky, which we'll talk about later, and then wind speed as meters per second. Most of these are standard measurements for parameters collected in the field. So I wouldn't worry too much about that, but it's up to you to ensure that the data you are using have these units, and you may have to go through and convert them before using EBASE. Okay. All right. So, like I said, EBASE works really well with swamp data because you all at the NERS collect this information already. However, because of the problems associated with weather data and water quality data being collected at different locations, you have to combine them before using EBASE. But I just want to go through use of this Swamper package real quick to show you how you import swamp data, and then we'll combine it for use with EBASE. This package is something we wrote almost 10 years ago now, so it was one of the first packages I wrote. It's kind of janky. Apologies for that. This is when I was first learning how to, build our packages. But the thing that I have found works really well, and that I think most people use it for, is really just importing swamp data into R. So there's a function called import local that is meant to work with zipped data downloaded from the CDMO. Okay, non-NERS folks might not know what that's about, but basically, if you go to the central data repository for the NERS, the CDMO, they have a download feature called zip downloads, and basically, you can download all of the NER data from here if you want, but you go through this process and you get after you make your request for the location, you get where am I? A zipped file with the data that you've requested. And all you have to do with that zipped file is put it in your RStudio project, and RSwamper using the import local function will do the rest for you. Okay. So we're going to do just that. Basically, that data folder where you've got that zipped file, there's a bunch of water quality data from Apalachicola. Okay. This is the data we're going to use for today. There's a couple stations at Apalachicola. There's Dry Bar, East Bay, Cat Point, I think is in there. But basically, I've downloaded data from 2017 through 2019 for several sites at Apalachicola to use with this website, and I downloaded it with the zip downloads feature. So if we wanted to import this data into R, and again, I'm operating on the assumption that you've got this in your data folder already, you would do so like this. So you've got Swamper already loaded with the library package. I'm just going to import Apalachicola Dry Bar. and it's going to be for the water quality station. So I set up my import local function like so. I would point it to where that zipped file is located. And again, because this is an RStudio project, we can use a relative path. So we don't have to say C:// whatever. You can just use the path relative to where the project is set up. So data is in the root directory here. And then I'm going to say this is the name of the zipped folder. And I have to tell it the station code for the files I want to import into R. So this is the station code for drybar. All NIR sites have similar naming convention. And then if I run that, it takes a second because it is unzipping the file for you. But then we have basically all of the water quality data for that site imported directly into R from that zipped file. Okay. Yep, so that's what I did there. Looked at the data set. This is what most swamp data looks like. It's 100,000 plus rows, covers the years of data that we looked at. So we can be confident that that information has been imported now. If you didn't see any errors, and if anybody has any issues getting this in, let me know, and we could troubleshoot it. The other thing we need to do is, let's see, we need to clean up the data. So thankfully, due to the rigorous quality control procedures that the CDMO uses and that the swamp techs follow, there are numerous QA/QC flags that are included in the swamp data. And it's up to you as the analyst to determine which flags you want to keep. If you go to the CDMO website, you can see what all of those flags mean. In practice, you probably just want to use things that have a QA/QC flag of 0. But just for sake of retaining more data for the examples, I'm going to keep all of the data that has 1 through 5, so positive values for the flags. There's another function in Swamper that will let you filter the swamp data based on the flags of your choosing. So I'm going to run that. It's called the QA/QC function. By the way, I've got Copilot, some AI nonsense running. If you see autofill for some things on my script, it's from Copilot. That you can, I think it's like a couple dollars a month, but it's pretty cool. It kind of cheats for you, but if you're wondering what that is and why it's popping up, that's why. Okay, so QA/QC. Basically, there's one argument, and it's going to be the flags you want to keep. So we have QA/QC keep. I have to specify 0, 1, 2, 3. I could type 4, 5. Okay. Now, if we run that, what it's doing is basically any flag or any observation that has that QA/QC flag, it's keeping those. And every other one, it's assigning an NA to that value. So if it has a -5 or a -4, that observation gets an NA. If I were to look at actually, I'm going to call this clean just to show you. Ooh. So APA DB WQ clean. If we look at the number of rows and columns in this compared to the original one before we ran the QA/QC cleanup. Jesus, there we go. It's the same amount of rows. So here's the number of rows in the clean one. Here's the number of rows in the original one. Far less columns in the clean one. So if you look at the clean one, you'll see that now all the QC flag columns are gone. We have still all the same parameters, but essentially anything that was given a flag that is not within QA/QC keep is going to be an NA. I don't see any here other than things that already have NAs, but you can rest assured that if you run this function and use the flags you want to keep, those values will be retained, others will be excluded. All right. That's pretty much it for that function. Yeah. Oh, yeah. So we also have to import weather data. So because I said EBASE and other metabolic approaches require both weather and water quality data. So what we're going to do now is import data from the East Bay Meteorological Station. And so you would follow basically the exact same process that you would do for the water quality data. Okay, I'm just going to copy and paste that code. APA met. Okay. I'm going to change the name of the object I'm assigning it to, keep the path to the zipped file the same, and then the station code, I'm going to change that to EBMet, East Bay Meteorological, and then import it. Takes a second. Okay, and then we could see, of course, I named it wrong. APA. My naming is off today. Let's do that again. And there's our weather data. So same, sets of years that we requested from the CDMO as the water quality data, 2017 to 2019. We got air temperature, humidity, barometric pressure, wind speed, which is the one we need for EBASE, and sort of the same setup too, where you have QA/QC flags in the raw data. So let's clean it up. We'll use the QA/QC function. We'll use the same flags as before, and then we'll run that. And we'll look at it again. And so same deal. Basically, all the flag columns are gone. Things that we wanted to keep are kept, and things that we don't are assigned an NA. So again, QA/QC will never remove any rows. So you'll still have the same continuous time step. It just assigns an NA to particular values in a row column combination for the different parameters. All right, so pretty straightforward. This I think will save you a lot of work from importing the files by hand. If you weren't using Swamper, as most of you know, Swamp files come as 1 year at a time, so you'd have to import each one and then stitch it all together. This combines it all for you, and it deals with the QA/QC flags at your choosing of which ones you want to retain and keep. All right, the last thing we have to do is combine the data, okay? Because EBASE only requires one input data frame to use that includes both water quality and weather. So there's another function in Swamper, and this is the last one we'll use, called the comb or combine function. This is effectively just like your standard joining functions you might be more familiar with from tools like dplyr. It's just one that's developed specifically for swamp data. So there's a couple things to recognize when using this function. I forget all the arguments for it, but the two important ones are time step and what method you're using to combine the data, okay? I forget when Swamp switched to this, but they are now collecting data every 15 minutes. Yes. In the past, I think it was every 30 minutes. But you can basically specify what time step you want the combined data to be simplified or kept the same at. And so in this example, we're combining the water quality data and weather data at a 60-minute time step. Now, remember, if it's 2017 to 2019, these are going to be 15-minute observations. You can keep those. You can just say time step equals 15. But just for sake of the examples in this workshop, we're going to use 60-minute time step just to speed it up. And in practice, 60 minutes is probably just as good as a 15-minute time step. You're not going to get wildly different results, but it's my advice to keep 15 minutes if you have it. It's just for the examples herein, we're gonna simplify it down to that time step. And then the combination method is also something to consider. So like say you're trying to combine two time series where it's the range of times don't overlap. Maybe you have 2014 to 2017 and then 2015 to 2019. How do you combine those? Well, if you use the union method, it's going to keep the entire range of time that are shared between both data sets. There might be good reasons for doing that or not doing that, but there's other ways to deal with that. So if you used method intersect and you have two time series where again, they're covering different ranges of time, but there is overlap. The intersect method will only keep the ranges of time that overlap between the two time series. Now, for this example, it doesn't matter at all because these are 2017 to 2019 for both the water quality and weather data. So whether you use union or intersect, you're going to get the same results. I just wanted you to understand the differences between the method if you are combining time series that have different overlapping lengths of time. I think if they're non-overlapping, it'll still combine everything. You'll just have a bunch of NA values for the parts that don't overlap between the respective data sets. So let's do that. Let's combine them. Combine swamp data. And I'm just going to call it APA-DB, just as a nod to the fact that it includes both water quality and weather data. Use comb, APA-DB. Actually, I'm going to recreate this one just for consistency. So I'm using the cleaned data set, the ones that don't have QA/QC. I forget, I think Calm might give you a warning or an error if you try to do that, if they still have the QC columns. But, those are the two we're going to combine. Method equals union times step equals 60. And then that should be all we need. And then if we look at that, there we go. So we got everything together. You'll see the time step is now every hour as specified by that. And we have both water quality up to here, and then weather data in the remaining columns. So we're almost there. We are almost ready to use EBASE. So yeah, it's pretty easy with Swamper, and it'll get you 90% of the way there. In the interest of time, I'm gonna ask a question. Do y'all want to do an exercise now, or should we just blaze forward? How's everybody feeling? Everybody's asleep. Okay, so I got two people saying no exercise. Okay, and then Ethan says in 01 or 02, they switched from 15-minute, 30-minute sampling. All right, yeah, so nobody wants to do the exercise. That's fine with me. It's kind of boring. It's the exact same thing we just did, just with a different water quality data set. Okay. All right. So now a few more steps before we're ready to use EBASE, okay? So if we look at the example data set, you'll see that we only need 5 parameters, and the naming convention kind of varies a little bit, right? So because R is not intelligent, it needs exact column names to use the data. So this is our data set we've created, right? So this is everything we've combined. We need to remove extraneous columns and rename them. If you're basically familiar with dplyr, this is really easy. So next we're going to do just that. Let's see, select and rename columns. And I'm just going to give it the same exact name. If you've loaded the tidyverse up here, this is the whole collection of packages within the tidyverse that do a lot of useful things for you. dplyr is part of that. dplyr is a data wrangling package that has all sorts of useful things in there for manipulating data, and it's like my go-to for any sort of data munging prior to any analysis. But if you load the tidyverse, the dplyr package will already be available for you. So we'll use a function. I'm going to use pipes. I'm hoping people are familiar with that concept. If not, look it up. Super handy. But you can use a pipe to pass one object to a function, and et cetera, et cetera, et cetera. It basically means this object. My stupid Copilot. I'm going to have to turn that off. I'll do that during the break. But basically, this says take this data object, pass it to select, as opposed to writing it the other way. If we did select APA, DB, and then all the other arguments. The pipe is, to me, a more legible or more perceptible way of reading our code, because you do one thing, then another thing, then another thing, as opposed to stacking functions nested within one another. So anyway, use a pipe, and I'll try to keep the use of pipes down to a minimum. But basically, I'm going to select the columns I want. Actually, I'm going to turn that off right now. Bear with me. Okay, now it'll be less distracting. So, okay, these are the names of the columns I want, or the columns that I have. If I did the example data set, this is where I'm trying to go. So you can select and rename columns both in the same select function. So if I want date time stamp to be named date time stamp using the correct case, I could do that. So this simultaneously renames and selects that column. Do the same thing with DO. DO observed is going to be from DO MGL and the swamp data. Temp, and this is water temp, not air temp, so will be temp. Salinity will be from the sal column. Par will be from top par. And then wind speed will be from wind speed. Okay, so let me run that. APA DB, let's look at it. Now it looks a lot like the example data set. Right column names, right names. I could even verify that the names are the same using a simple logical setup. If I run that, we see, hooray, they're all the same. If you really want to convince yourself that they are. Actually, one I forgot to retain, I'm going to keep the the depth column as well. This is not required as input in terms of the continuous depth data, but you do need to know water column depth at your site when you're using EBASE. So even though it's not required as input in the input data frame, it is good to retain that just as additional data that you will use. So actually, I got to recreate that, and then I've got depth. Okay. There we go. So same as before, but now we've got depth. And if I were to, yeah, it won't let me do that. So do it that way. So we see that actually this guy, if you're not familiar with that operator, basically just it's like a set comparison as opposed to one-to-one equality comparison. So are these names, any of them, in names xstat? So we see yes, 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 except for, of course, depth, which, like I said, we don't need, but it's good to have. Okay, we're almost there. So we've selected and retained the data we want. Again, EBASE, it's case sensitive. It does require the correct units. And again, that is up to you to make sure your data have the correct units. And that is what we will tackle next. So like I said, so this is the fun part. So DO has got to be milligrams per liter. That is what Swamp measures and records DO as. Temp, Celsius, correct. Salinity, PSU, correct. PAR is something very strange. Millimoles per square meter per 15-minute logging interval, or 30 minutes if you're using earlier Swamp data. EBASE requires it as watts per meter squared. So we're gonna have to convert that. It's kind of an unintuitive one, and I had to bug Jill about the conversion for this, but it's essentially this conversion factor here. So if you want to go from micromoles to meter squared, or micromoles per square meter per second to watts per square meter, you've got to use this conversion factor. There's a couple other things too. First, we have to get from millimoles to micromoles, and then per 15 minute to per second. I don't expect you guys to remember this, but this is something, if you're using Swamp data, this conversion is something you absolutely have to do. Before I go on to that, also I wanted to say wind speed is correct. That's meters per second in Swamp. Also what is expected by EBASE. And then depth is also expected to be in meters. Okay, so to go so these are the units that is currently recorded for PAR in Swamp. So millimoles per square meter per 15-minute interval. We've got to multiply it by 1,000. So going from millimoles to micromoles, divide it by 900 to get from 15 minutes to second, and then multiply it by this factor, which I'm assuming Morell and Smith knew what they were doing, to get micromoles per square meter per second to watts per square meter. Okay. This is probably like the most complicated part of the workshop. But basically, you could do that in one fell swoop. Just copy this code. I'm going to use the mutate function from dplyr. So APA-DB, we've selected the columns we want using the pipe, mutate. And mutate can be used to create columns or work on existing columns. I've never found the name intuitive for that, but you could think of it as like mutating parts of a data frame and columns. I don't know. But we want to mutate par and then use the conversions that I just talked about. So multiply by 1,000 to go from millimoles to micromoles. Divide it by 900 to go from 15 minutes to 60 minutes or second. And because we are, again, remember, we combined this to a 60-minute time step, That's irrelevant. The value measured, any observation in swamp is still going to be at that 15-minute, because that's where it was collected natively in that time step. So even though we are just subsetting to the hour, we still use that divided by 900 to account for the native time series. And then multiply it by 0.2 something, 2175. 2175. And then we should be good to go. So let's convert par from something terrible to watts per meter squared. Okay, now we should be ready to use EBASE. Let's look at it. So everything's the same except we've converted par. Yeah, so we're good to go. Now, just as like kind of a insurance or for your future self, it's good to save this data set because we're going to use it for the next lesson after the lunch. So let's just save it. And this, I like to save R data as a binary R data file. Unfortunately, this is a format that only R can read, but it's compressed, so it's very small. So you can share it more easily, and it imports really quickly if you have a much larger data set. So I've just gotten in the custom of doing that. You could just as easily save this as a CSV file if you want to go that route. That's just a text-based, comma, delimited file. But for this example, I'm just going to save it as a R data file. So we name the object we want to save. We then save it to a path in our project. So I'm going to call it R data right there and save it. You should be good as long as you get no errors. So once you run that, you should see it in your data file or your data folder in your project. Here I've got APADB saved 30 seconds ago. All right. So let's all do that. And then, yeah, the last thing we want to do is really just look at our data. You know, this applies to any analysis you'll want to do. Essentially, you know, don't blindly throw data at R functions without looking at them first to make sure they're giving you information you would expect. For swamp data, you know, the QA/QC flags should handle a lot of that for you, but just as general good practices for data analysis, just look at your data. It's not hard. It's fun to do. At least I think it's fun. And it can be really illuminating as to what's going on in your data. For this type of data, you know, like I said, the QA/QC flags will get a lot of erroneous values for you. Outliers, I think, you know, that's more of a personal decision on what you call an outlier. That's a whole other issue or challenge in terms of how you measure outliers and what you do with them. I don't want to really talk about methods for doing that, but just be aware that outliers are commonly assessed and dealt with accordingly, depending on your preferences. But the bigger issue for swamp data is missing observations. Most R functions will, well, I don't want to say most, but I think conventionally in the past, most R functions will just fail if there's missing data. Other approaches to do it is to handle the missing data in some way, whether that's obvious to the user or not, depends on the package or what function you're using. Like think, for example, like the mean function. If there's NA values in there, if you're taking the mean of a vector of values, it will error out for you. It'll say, I don't know what to do with NA values. At least I'm pretty sure what that, yeah. So let's see. Let's make a made up data set with an NA value. If we do mean of that, it'll give me an NA. It won't error out, but it'll just say, I don't know what to do with this NA value. So you have to, so in this case, it's not telling you what it's doing. You have to look at the help documentation and see that, oh, there's an argument called NA remove equals, or NA remove, where I can tell it what to do with those NA values. Basically saying, remove those values and then give me the mean. So 135, the mean of those is 3. EBASE is in that category of handling missing values for you. I'm going to talk about later what it does to missing values and how you might use results that may or may not contain estimates from missing data, okay? But before we even get there, it's good to just look at the data, like I said. So I want to just get a sense of like, I'll type this out, but how many missing values there are in my data set. So count the missing values. So this data set, remember, has 26,000 rows. We can use a nifty function that comes with base R called apply, which can apply a function across all of the columns or all of the rows in a data set. It's a nice little convenience wrapper function. But basically, you can say, I want to run it on this data set. I can say 1 or 2 to say whether I want it to do the function on rows or columns. That's going to be in the help documentation for that function. And then I could say, run the function, run the mean, whatever I want. But I'm going to make a custom function here that basically just counts the NAs. It's a generic function that counts the NAs and then, well, yeah, it just counts the NAs. So if you're familiar with the way to make a generic function, it's really handy. You just use the function X code, and you could say, do whatever I want on X. So X is a generic placeholder. I could just as easily define this outside of the apply function and then put it into apply if I wanted, like so. But really all this is doing is it's wrapping two existing functions in R. Is a value NA or not? That is a function that comes with R, and then summing those values up. So this will return a true false vector. And if you run sum on a true false vector, it'll sum everything that is true. So we'll run that and we'll see basically for every column how many NA values there are. Date timestamp, none, because this is continuous in time. DO, 6,000, temperature, 6,000, salinity, 6,000, PAR, almost 8,000, wind speed, depth. You get the point. So there are huge gaps in this data set. And because this is 2017 to 2019, those of you that live in Apalachicola probably know what those gaps are from. I will let everyone else come to their own judgment as to why there are huge gaps in some of the years. But let's plot the data. I want to see, this just tells us how many gaps. Let's see, Theo's getting huge gaps, more than what I got. It's a good question. I don't know. Try creating the APA DB data set again if you want. Let's see if live coding is caught up. Sweet. Yeah, so what I would try, Theo, is running all of this code again and seeing if you still get the same number of missing values. Yeah. Okay, so like I was saying, this will tell you how many you have, but not where they are in the data. So we can plot them, and we're going to use the Plotly package in R. If you're not familiar with that one, that will basically create your standard line plots, scatter plots, but the plot is interactive, and it's really useful for swamp data because you have thousands of observations, and you can zoom in and see, look more closely at where those gaps might occur. So you've got Plotly loaded. you basically run this function called plot_Lee. Your data is going to be your APA DB data set. And then I forget the syntax for it, so I'm going to go back to my cheat sheet here. You define an X value for the X-axis, a Y value for the Y-axis, what type of plot, and how the observations are displayed on the plot. So type scatter mode lines, let's see, X equals, and you have to use, Plotly's weird, you got to use this tilde notation to say it comes from the input data set. We're going to do Y DO observed. Let's see, type equals scatter plot, mode equals lines. So scatter just means XY standard plot, and then the mode is going to be the how the points are displayed. So this takes a second to run and render, but we can see here are all our DO observations for that 3-year time period. And you can mouse over it. You can see, okay, here's the value on September 25th. It's 6.6 MGL. So that's kind of cool. But what's really valuable about this is you can drag and look into the time series to see one window of it at a time. And these controls at the top will let you mess around with it too. You can, drag, look at it. So it's really great for exploratory analysis. But again, what I want to draw your attention to is this gap. So let's just have some fun with this. Let's look at wind speed. Whoa, look at that. 22.7 meters per second. And then a bunch of garbage data. Ethan, what happened right there? Ethan fell asleep. This was Hurricane Michael, I believe. Yep, Paul says Michael. So
that might have been where the anemometer maxed out and then continued to go beyond its capabilities before the entire station was washed away.
Yep, pretty much. So this was a hurricane. You could see it's like, oh God, it's coming, it's coming. Here it is. And then I think it like falls over and is like slanted at an angle. So these are garbage data. But basically this entire station was out of commission for pretty much almost a year. So obviously, what does that mean? I would not evaluate metabolism anytime in 2019 if my goal was to evaluate metabolism at an annual scale. These values are probably legit. They're probably good. These ones right before, not good. So I wouldn't evaluate metabolism in this time period. As you'll see in the examples later, oh, here's some more gaps. I have no idea why these are present, but this is this is like a week or two gap. But yeah, this gives you a sense of where the gaps are, why they may occur, and if you're going to go on and evaluate metabolism, which years you may or may not want to evaluate, and what is your question? Is it like, I want to look at daily metabolism? If that's the case, 2019 after, August 12th or so might be okay. Probably okay. I would ask Ethan. But yeah, Plotly is great for this, for interactive analysis. Strongly encourage you to use it as a tool, especially for looking at really long time series. Okay. We're doing good on time. I just want to mention one other thing. We'll skip the exercise, I think. Any questions or comments about that before I just quickly talk about other data? Jill's got to leave. Thank you, Jill. All right. No questions. Good. So, like I said before, you can use EBASE or any open water method, obviously on any continuous monitoring data. I started with Swamp and Swamper because I know a lot of you are from the NERS. Those of you that are not, you can use the NERS data if you like. It's a great wealth of information, but obviously, you might have your own monitoring station or other places where you're getting continuous data and you want to estimate metabolism. The steps are almost identical. You import water quality data, you import weather data, you combine them, you look at the data and see, are these values legitimate or not. You may or may not have QA/QC flags depending on your data you're using. Obviously, it's up to you as the analyst to determine what's a bogus value. But I leave that exercise up to you. So I just have an example here. This is from Tampa Bay. This is from one of just a handful of continuous monitoring sites in Tampa Bay. We've not been continuously monitoring water quality for a long time. It's just been a few years now. But there's a monitoring platform. I believe it's lower Tampa Bay, approaching middle Tampa Bay, where you can access their API to programmatically import data from that site. So I'm just going to copy this for you just to show you how easy it is. Let's see, Tampa data. So their API is set up where basically you can read in a URL where that URL has the query that you want to use for whatever data you're interested in. So here's like the core URL, but you'll notice the way it's set up. So you have this min date component that specifies the start date I want to pull, the max date I want to pull, and what parameters I want to use. So again, this is for EBASE. I want to pull in if this is water quality, pull in salinity, temperature, oxygen, and PAR data. And because I'm going to be using a pretty basic core R function, I want this returned as comma. Actually, I think this is tab delimited text file. So I'm specifying the output format. If you were to actually go to this URL, you can see the data, I believe. Oops. So this is what an API does. It basically just serves up data through a web request. So R can access this directly, and you could programmatically change the start end date, what parameters you want, whatever. It's super convenient. But basically, we can use that URL, use read table. It's the Lobo. The name of the platform is Lobo. I forget what that stands for. Something observation. But once we read it in, there's our data. So piece of cake. Wonder if I can do that. Yeah, so now I just changed the start date argument, and now I have data starting in June instead of July. So super, super simple. CDMO has an API. I haven't used it in a long time, but I remember it being limited in the requests that you can make. But those of you that work at the NERS might look into that as a means of pulling data easily. At any rate, this is just water quality data. So we want to get weather data. We can use, there's several NOAA ports stations in Tampa Bay. The closest one is going to be in Port Manatee. And so they also have an excellent API. I'm going to similarly retrieve that data. Their API request is you specify begin date, start date, what station you want, time zone, all that fun stuff. So there we are. Again, we just need wind speed for EBASE. So when we subset and combine the data, I will only retain wind speed. Yeah, and then the rest of it is just basically going through the process of renaming the columns, selecting the columns, making sure the units are right. Let me just get this set up so you have it in the live chat. So this is, again, the same thing we did before, selecting the columns with the right names, making sure the units are right. I think there's there's one other important thing to know about importing your own data. Where am I? Oftentimes when you import data from a text file, and if it's a time series, you need to manually convert that time series to a date time object in R. Swamper will do that automatically for you based on the location of that station and its time zone. But if you're importing your own data into R, you need to make sure that time zone is correct. So if we look at the Lobo data, the structure of it, and show the same thing for ports, you'll see that it's a character string. This is not a date time object, and EBASE will not know what to do with this. So we have to convert that to a true date time object. The Lubridate package has many useful functions for doing this. This comes with the tidyverse. Here I'm just using the notation that lets you use a function from that package without actually loading the package using the library function. This is oftentimes convenient if you only want to use that function one time in your analysis. But basically I'm saying this is the format of the date, time, and character string from that observation platform. Year, month, day, hours, minutes, seconds. You can see that down here. Year, month, day, hours, minutes, seconds. There's other functions in the package. It's like month, day, year, minutes, hours, whatever combination you have for that character string, there's a function for it. So if I use this function, because that's the format it is, and then specify the time zone, and in this case, I'm using a time zone that is Eastern, the time zone we're in, but without daylight savings. So most monitoring platforms, I think this applies to the NERS as well, do not use daylight savings just for consistency of the record. You can look these time zones up on Wikipedia, but this is the one I use all the time for Eastern time zones without daylight savings. So this will convert it to the correct object, and we also have to convert par. Now, if you go online to this Lobo website, you'll see the units for par. These are not the same units as from SWAMP. It is really just millimoles per meter squared per second. And to convert it to watts per meter squared, all we have to do is just use that single conversion factor from before. So that's why I'm not multiplying it by 1,000 and dividing by 100. Yeah, so let's read that again. Let's see. Yep, so yeah, now date time is correct. It's a date time object. Par has been converted. We're good to go. I will stop there because I want you all to take a break. But the last thing I'll say is that we have to do the same thing for the ports data, the weather data. We have to convert date time to date time, and then we have to join the data. And in this case, we're using a join function from dplyr, which basically is a lot like it's kind of like union, but it uses all of the time series observations from the water quality platform to join by date time. And we end up with basically the data object we want. Water quality data at hourly time step plus wind speed from the ports data. And that's it. Let's see. Yeah, John says land, ocean, biogeochemical observation. Thank you. That's Lobo. All right, cool. So all that is to say it's the same steps, no matter what data set you use, combining water quality weather data, making sure the column names are the same, and making sure the units are correct, and that's it. You should be good to go. Any questions on that before I let y'all go for a little break? Okay. Well, we will reconvene back here at noon Eastern time. If you're want some punishment, you can do the exercises, but I don't encourage that. Eat some food, take a break, whatever. I will see you in about 24 minutes. All right, everybody, give me a thumbs up in the chat if you're back. Or a hi or whatever. All right, well, we got a majority of people, I think. So we'll keep going. I hope you had a good break and were able to recollect yourself and are geared up for the rest of the workshop. Um, so, yeah, like I said before, we have this room till 3, or this chat till 3. I don't anticipate going that long. The rest of this will basically be an overview of EBASE, how it works, and then some interpretation. Then at the end, if we have time, or if there's desire, we can go through some examples of potentially real world questions you might ask of data, and hopefully give you some greater insight into how this information is useful to evaluate ecosystem status. But if y'all just want to have the rest of your Friday back at the end of this, that's totally fine too. I'm fine either way. Okay, so I think we're all caught up on the live coding script. Yes. We are, let's see, let me clean all this up. Okay. So now we get into EBASE. Okay, so this, like I said before, if you go to the EBASE package website, which I did put in the chat earlier, but I'll show you again. This content that I've got for the next hour or so is 90% of it is from this vignette article, which is on the EBASE package website. I think there might be a little bit more detail on this vignette, but hopefully us going through most of the content today will be a little more accessible way to understand how the package can be used. I'll just drop that link in the chat if you need it. All right, so the first part of this is going to be a bit of discussion or description about how the method actually works theoretically. And then the rest of it will be actually using the R package to run some examples. Really kind of, it's really simple to use, but really it's more about how you use it and how you interpret the output, both in assessing model fit, as well as making inference about drivers of ecosystem change. So if you remember, before I forget to, how is give me a thumbs up or what, but how is the pace? Am I going too fast, too slow? We do have a bit of time to work with here, so I can slow down if people are getting lost or what. I'm getting a thumbs up from Jennifer. John says good. Okay. All right. Well, I'll just carry on then. So our first lesson, the introduction, was basically an overview of what metabolism is. Remember, I said that if you only leave this workshop remembering one thing, it's the definition of ecosystem metabolism, the balance between processes that produce organic matter and those that consume organic matter. That's it. It's pretty simple. But it gets complicated when we try to infer those rates using time series or other methods, where we might have incomplete information about all of the things that influence metabolism change. So I'm starting there from where we were in the introduction of what metabolism is, just to sort of expand on that to show you how EBASE is really all that, or not all that different from the core idea of these open water techniques. So here's your basic equation. Net ecosystem metabolism is the balance between production and respiration. And of course, we can estimate production and respiration by leveraging time series data from dissolved oxygen, where it's basically a function of what is the rate of oxygen change per unit time as an areal unit, again, multiplying it by depth, and then breaking that out using a simple mass balance equation where that difference is going to be related to production, respiration, and gas exchange as an alternative expression of how oxygen might vary in the water column, or an additional expression rather. So this is the scariest, I'm sorry, second scariest or first scariest, I don't know. Take your pick, but this is the EBASE equation. It is kind of intimidating at first, but you'll see I wanted to put it right below the one up here to show you the pieces and what they represent, because all it is really just that production, respiration, and gas exchange. So the component on the left is the same. So it is simply based off of the change in oxygen concentration per unit time. But production is going to be a function of PAR, so light availability, as well as this parameter A, which I'll explain in a second. Respiration is just respiration. There's nothing fancy about that one. And then the remainder of this is where it gets a little complicated, and really is why you require other components like salinity and wind speed and whatnot as input to EBASE. So this is, like I said before, if you remember the simple demonstration of gas exchange and how that's basically expressed by most models. So here's gas exchange D. That's going to be a function of the difference between oxygen concentration and the DO saturation concentration. How big is that gradient? If it's large, you'll get more gas exchange, as well as this parameter, the gas exchange coefficient, which allows that gradient to vary by other factors beyond just oxygen and the saturation concentration. So in EBASE, it's the same. So this is that difference between DO and oxygen saturation. And the rest of this can be thought of kind of as the gas transfer coefficient. But there are a couple pieces here that are important. There's the Schmidt number, which is unitless. There's wind speed squared. And then there's this B parameter, which I'll explain in a second as well. But I just want you to realize the pieces here and what they are. So production, respiration, gas exchange. We can get all of this information from the input data except for 3 of these parameters. So we have water depth, we have oxygen concentration, we have PAR, we have wind speed, and then we have the Schmidt number and oxygen at saturation, both of which are calculated from water temperature and salinity. The remaining parameters in this equation, we have to estimate from the data, and that's what EBASE does. So when you feed input into the function, it runs through this process to estimate the parameters A, R, and B. And going back to what metabolism is, your primary interest is going to be in production, which is A times PAR, respiration, and the difference between the two. But I wanted to explain these because they're important in and of themselves for evaluating how and what affects metabolism. So like A, for example, we call this the light efficiency parameter. The higher this value is, the more sensitive production is going to be to light availability. So highly productive systems might have more higher A values, and comparing this particular parameter between systems might be a useful way to understand production overall and how light availability affects it. R is just respiration. That's just, there's nothing fancy about that one. Some other models make this as a function of temperature. We kind of decided against that, which I don't remember why, but it's in the paper. And then B is the sensitivity of gas exchange to wind speed. So again, if this is a higher value, you might expect that particular location to have higher gas exchange per unit of wind speed or wind increase. So this would give you an idea essentially of how important gas exchange is overall for the DO time series. So is it a big component or a large component? And I think generally speaking, gas exchange in estuaries is not particularly large, but other systems, it could be a pretty dominant component that you really have to constrain and estimate accurately to evaluate production and respiration. So the entire crux of this project is really how do we get accurate estimates of A, R, and B? Because without these, we cannot accurately estimate ecosystem metabolism. So a lot of open water techniques might vary in how these particular pieces are parameterized. We chose this particular format, and this is, I should say that we adopted EBASE from a similar method called just BASE that was developed for streams. And we modified a lot of the core components of that equation using parameterizations that we thought were more appropriate for estuaries. Like, for example, this entire gas exchange component is wind driven, and it was developed for open oceans. Whereas the original method for streams did not have any wind dependence on gas exchange. So simple changes like that. So we paid homage to the original method by still retaining the base name, but just attached estuary on top of that. Okay, so just remember, A, R, and B are going to be the ones that are estimated from EBASE. A relates to production, R is just respiration, and B is important for gas exchange. And you also get, the P and R estimates by themselves as a combination of the different parameters. The other thing that makes EBASE really useful is not just the model that's been adapted for estuaries, the core equation, but how the parameters are estimated. Now, I am not a statistician. I'm especially not a Bayesian statistician. So my description of how this works is probably pretty rudimentary, but I think if you understand how it works just enough to be able to understand how and why you might modify the model estimation process, that's sufficient for understanding how the estimation process works in general. So those of you that are really, I guess, or that have had any stats lessons, you'll know that there's typically two camps when it comes to hypothesis testing or just model generation stats. There's conventional frequentist approaches that everyone is taught as like a first introduction into basic stats. These are all probability based, like t-tests, linear regression. Those are all pretty simple things where you're basically testing a hypothesis and then fitting a model to it. On the other hand, you have Bayesian techniques, which are kind of the opposite. It kind of turns that general paradigm around and says, well, what is the likelihood of these data given the model, as opposed to fitting a model to data in a frequentist approach. And I'll try to link that to EBASE in a second to make that part more clear. But the key is it departs from this simple p-value alpha statistic approach where it's a binary yes no and evaluates likelihood of an outcome as a distribution. And you may or may not have information about that distribution prior to the modeling component. As far as the core idea behind Bayesian statistics in general, at its very, very basic level, you have Bayes' theorem, which if you've ever been in intro stats course and they talk about Bayes statistics, they will show you this theorem. Modern techniques for Bayesian statistics are more complicated, but I'm pretty sure they all sort of derive from this basic idea. And this approach basically says, well, what is the likelihood of me observing or just observing something given that something else has occurred? So it's a conditional likelihood formula. Because, you might say, well, why is it hot outside today? And that's because it's July. So the likelihood of it being hot really depends on the season. So this formula, this Bayes' theorem, sort of describes that in a formal sense where you can calculate likelihoods of knowing an event or how an event is likely to occur if something else is present. So if I know it's July, that's prior knowledge. It's already, a component that would influence my decision on whether or not it would be hot outside. So that's a conditional description of, how I would describe the temperature given other information. Now, what is this other information? So most Bayesian statistics, they require a declaration of something that's called a prior distribution. So what is my prior knowledge about past events or other information about the system I'm interested in? So we have to specify in any Bayesian approach this prior distribution. Now in EBASE, there's default priors, so you don't have to choose them. I'll talk about why you might want to change them, but they are used as input to the model. So remember, EBASE is estimating A, R, and B. So because this is a Bayesian approach, we have to give the model information, prior information about what we think likely values are for these parameters that the model will estimate. Well, what are these likely distributions? So how do we define them? We actually looked at the literature. We went to Jane Caffrey's old paper for the most part. And because she had already gone through the process of estimating metabolism at these locations, we were able to infer likely values for these parameters in the ranges that would likely occur across estuaries in the United States, which might apply to, temperate subtropical estuaries around the world. Now, this is what these prior distributions look like. There's a function in EBASE called prior plot. So I've already got EBASE loaded. I'm just going to run the function. You don't have to give it any arguments. And these are the default prior distributions. And so, of course, being distributions, there's a central tendency and a spread around that. Because these are just normal distributions defined by two parameters, mean and standard deviation. These are likely values we estimated for A from Caffrey's work, same for R, and same for B. And you can see the units associated with each of one of those. And these are crazy units, mostly because of how the formula, the core model formula for EBASE is put together. So I wouldn't necessarily know how to interpret that, but it works out once they're all multiplied together to a rate of millimoles of oxygen per square meter per day. So I wouldn't worry too much about these units, but just understand that these values, these prior distributions are based on the literature. And they are truncated to be, greater than 0. The B parameter is truncated to be within 0 and 0.5. But for the most part, these are fairly wide ranges of which the parameters could be estimated given this information. So you don't have to specify that. You can change it if you like, and we'll talk about that. But this is the prior information that's given to the model when EBASE is estimating these parameters. Now, I said that we got these values from the prior literature based on ranges in Caffrey 2004. You might argue that this is an informed prior distribution. In other words, we had prior knowledge of what these values could approximate to. There's a distinction in Bayesian statistics between distributions, prior distributions that are informed or uninformed. I would consider, even though we use the literature to develop these ranges, that these prior distributions are uninformed because there is a relatively large spread of values around this. And so this allows, when the model is being fit, to sample from these distributions to then estimate what the DO is after we've sampled from these priors. And then what is the likelihood, in other words, what is the posterior distribution of those estimated parameters after we've sampled from these prior informations over and over. And that's where the Bayes' theorem comes in. So what is the likelihood of this parameter that I've then estimated from the data, given that it was coming from this previous distribution? So there's a bit of a connect there. It's a little abstract, but it's comparing knowledge it already has to estimates that may be improved given the data that it's presented to the model. So that's it in a nutshell. If you have the other benefit of this, so I say these are uninformed, right? Because there's a wide range of values within which these parameters could be chosen. Now, if you have more information about what these values could be, say you know that in your particular estuary, you know that respiration is exactly 200 millimoles of oxygen per meter squared per day. You could tell it that this is the prior information I have and that I am going to use 200 as my estimate without any wiggle room around that. And that's what will be returned by the model. And in doing so, you give a little more degrees of freedom to these pieces to be estimated from the data. So there's value in having prior information because you can oftentimes get more accurate estimates of the posterior distributions of these values. Yeah, and then let's see. Steven says, let's see, another useful way to think about prior choices is in terms of strength. Weakly informative priors are easily overcome with the data, but strong priors have much more influence on the model results. Exactly. So yeah, if you have a informed prior with very small ranges around that, that gives the model, I guess, less flexibility to have variable outcomes for the other parameters. Is another way to think about it. So I'm presenting this because I want you to understand just the basic theory about Bayesian approaches, but also understand if you have additional information about your system, you can use that to create a potentially better fit of the model to your system. The last thing I'll say about it is EBASE uses the particular Bayesian approach it uses is called MCMC, which are common approaches for these statistics. This stands for Markov Chain Monte Carlo, and it's basically a stochastic way to sample the prior distributions repeatedly multiple times until you get a convergence towards a very likely estimate for the posterior distribution. So this is the part where I get a little, it's a little black boxy to me, and I don't necessarily understand all of the pieces that are used underneath the hood. But it is a robust way to estimate posterior distributions. And it does, unfortunately, increase the runtime of model estimation. So like the ODM open water method, that's just the bookkeeping approach. You could estimate metabolism in seconds with, standard software. This one does take a little bit longer. There are ways to get around that, which we'll get into, but I just wanted to warn you guys, if you do run EBASE on a time series longer than a month, it will take a few minutes. If it's years, it could take hours, but it's not insurmountable. Okay. Does that make sense? Does everybody understand? Okay. Now we are going to use EBASE. We are going to start by loading the data set we saved in our data folder. So we will use the load function. Remember, this is the dry bar combined water quality and weather data at 60-minute time step, 2017 to 2019. So we use load and then just say file equals data, ABADB, our data. That should load no problem. And then, like I said, because EBASE can take a while to run, I'm going to subset a few days just to show you how the model works. And this will run in a couple seconds. So I'm going to use dplyr and define some dates that I want to look at. So what did I pick? March 7th through the 14th. Okay. First, I'm going to make a vector for the dates just to make the R code a little cleaner. So let's see, let's try 2017, 03, 07, 00, 00, and then the 14th would be the same, just change the 7 to the 4, 14. Okay, now we can use lubricate, I believe. So I've noticed how I type this out. This is year, month, day, hours, seconds. So I can say year, month, day, underscore, hours, seconds. That's the corresponding lubricate function. And let's see, time zone, I'm going to say was America, Jamaica. So that's Eastern time zone without daylight savings. Hours, minutes. Okay, so let's make sure that's right. So these have to be in that format, because if we subset rows in the data frame by date time, it's got a subset by this something of the same class or units. So I'm going to say APA DB subset, and I'm going to use the filter function from dplyr. This basically lets you subset rows based on conditions, which basically equate to a yes, no, true, false state for a set of rows. Let's see. So we're going to say date time stamp greater than or equal to dates starting date, and date time stamp less than or equal to the end date. And I believe that should work. Okay, yep, so we got things starting midnight on the 7th and ending midnight the 14th. Exactly what we wanted. So that's almost 200 rows of data. So like I said, this should run fairly quickly in EBASE. So we've got that subset. And then the next step is to run EBASE. So EBASE is just one function called EBASE, but it's all lowercase. Let's just look at the help file. So these are all of the arguments that apply to EBASE. The only ones that you are required to enter is the data set you're evaluating, the water column depth, and the time step interval. You have to supply those when you run this function. The rest of this is there are default parameters, which doesn't necessarily mean you should use them. But some of them are pretty important, and we will talk about what they do. Just as an example, these are the prior distributions that are default from that plot that I showed you. And what these values indicate is the mean and the standard deviation that are used in that plot. So if you wanted to change those, you would modify the arguments. But at any rate, if we just want to get this running, we have to specify the data, the water column depth, and the time step. So let's say EBASE, the data is going to be APA DB sub. I'm calling this res for results, just the convention of habit there. The depth we can get from our input data, which is why I said you should retain this column. Even though you don't need that data set, you can use it to identify the water column depth. You can just enter a number into Z if you want, meaning you don't need the depth column if you already know this. But if you don't know this information, you could derive it from the data. So what do they call it? ZAV, ZVal. I'm just going to take this as the mean from the subset of data. And then add 0.3 or something like that, because I think the sensor is typically 30 or so centimeters off the bottom. Yeah, something like that. Yeah. It will vary by site, but I believe that this is more or less correct. Okay, because I didn't specify the depth. So average depth for these days is about 1.7 meters. So I could put this then as an argument. And then the interval is going to be, this is in seconds, I believe. So 60 minutes, this would be 3,600 seconds. And you might ask, well, why can't this be identified automatically from the data? Good question. I forget why I coded it that way. I think it's to force the user to be explicit when they define this. Like for example, if you can input a data set that has irregular time series. And if you tell it what the anticipated interval is, it will, I believe, interpolate to that time step for you. All right. So that should be all we need. Let's see, an interval is time step in seconds. And then we should just be able to run it. So it's thinking. And this is where it's accessing that JAGS software that you installed, without which EBASE would not work. Yeah, the model is actually run outside of R, but then re-imported, and then the results are synthesized. So that's running EBASE. That's it. You'll see just for a week's worth of data, that did take a few seconds. So you can imagine if you were to run this on multiple years, it would take hours. But I've done that. It's not insurmountable. It's just, it's something you set and come back the next day and maybe it'll be done. All right, so we got a few warnings. These are fine. You may have gotten other warnings. I think the examples here have a whole bunch of nonsense that it's good to understand what it is, but doesn't mean anything wrong has happened. This is just information about stuff that's loaded, namespace conflicts. These three warnings in particular, these first two are important to realize. This one last here is basically just saying it's estimating the model without using parallel processing, which is a way to speed it up. That's fine. It will just take a little longer. But these two are telling you things that EBASE does for you that are worked into the package that are meant to be. Yeah, Lindsay said 25 minutes per year. That's pretty good. Yeah, so it's telling you things that's done that are helpful to you, that are in there as a convenience, basically. So because you cannot estimate metabolism for any time less than a day, like why you can't, because the assumptions is that you're describing the diel oxygen curve throughout a 24-hour period, so you wouldn't get accurate metabolism estimates if it was just 6 hours of data. So the package will remove any days with incomplete observations at the end and start of the time series for you. And I think this one is just removing one observation here. So the 14th, which is midnight, which is inconsequential, but that's what that's when it removed, because that's what it's designed to do. And then it will also fill missing values for you. Let's see, more than one time step or missing values will be interpolated. So this scheme will interpolate values to a consistent time series. In this case, because we're just 60 minutes the whole time, it doesn't matter, but there are missing values in this data set. And so it interpolates those values for you just as a simple linear interpolation between time steps that do have observations, because the model will not work if you send it missing data. Now, what the model does with results from interpolated data depends on how much of that data is useful. And there's a default argument to say if interpolated values exceed 12 hours, we're just going to throw that data out. It'll run the model on those values, but we don't want to use that when we're evaluating metabolism on the back end. I'll explain this a little bit more in one of the sections, but all this is telling you is like, whoa, be on the lookout that there are missing data in your data set that may or may not be retained in the output. And the default value for retaining it is meant to protect you from horribly inaccurate results. And the basis for that I will explain in that section. Okay, so what is in this output? Let's look at the results. Excuse me. So you have, it's still organized by the native time step in the input. You have a grouping variable, which I'll explain in a second. But the important pieces here are DO mod, the A value, the B value, the P value, the R value, and the D value. These are all pieces of that equation that I showed you early on. And these are what's estimated by the model. Now, the other pieces you'll see is that for each one of these parameters, there's a low and a high value. So this is the 95% credible interval for this parameter, which is the Bayesian equivalent of a confidence interval. So what is my belief that the parameter is within these bounds? It does estimate the DO time series because it fits a time series to the observed data based on the values that it estimates from these other parameters. So you get a model DO in addition to a observed DO. The grouping column, I'll say that you have to define a period of time in your time series within which the model is estimated. By default, it will estimate the model at each for 1 day at a time. So it's running the model on March 7th, then on March 8th, then on March 9th, and you're getting different estimates each day. That's just how it works. This grouping variable defines which group of rows applied to that period of time. So that's a little abstract, but let me just show you. Let's see how to plot the results. So there's a really nice function that lets you plot the output immediately. If you use EBASE plot and use the inputs in there, you'll see the model results for metabolism. So these are instantaneous values at the same time step as the input data, but the units are daily rates. So that way you can just average within a day to get the overall average. But what we see is production in P or in green here, respiration as a constant. So this goes back to that optimization period, that grouping variable in the output. It estimates one value for the R parameter for every grouping variable. So each run of the model, you get one estimate for R. Same for A and same for B, I believe. Yeah. Yep. So this shows, yeah, respiration here. That's why you get that flat line. You get one estimate for that value per optimization period. And then gas exchange here. Believe positive values mean in-gassing, negative outgassing. I forget whatever. It's in the text, but this is how basically the flux of DO from the air-C interface. We could also run this plot as daily averages just to clean it up. In this case, we could say instantaneous equals false. And now you have daily averages. So we had about a week's worth of data. Now we have 1, 2, 3, 4, 5, 6, 7 observations here. Yeah, so just a way to look at the data. And these all sort of work out of the box with EBASE. Oh yeah, okay. So this is another odd thing about EBASE that I will include in a later version, but in doing all of this work, we realized we never actually put any M into the output for EBASE. It's such a simple calculation, we just didn't put it in there. But what if you wanted to plot it? You have to basically estimate it yourself, or not estimate it, calculate it, just subtract R from P and then plot it again. So I have in this this workshop some code that shows you how to do that. It's trivial, but note that I will in a later version of the package have that included automatically in the output. So what you got to do is just go, you'll use mutate NEM equals P minus R. That's it. Why didn't that work? Oh, res. Res, because that's our output from the model. There we have it. So if we wanted to plot that, let's see, we got to get fancy. This is going to be some more dplyr wrangling. But if we want to create a plotting object, let's see, we want to select. So I'm trying to show you NEM, P, and R together. P, R, NEM. Then we could make that long format. Let's see. Let's see. Oh, I didn't even do that. Let's see. Names from. Values from. Oops. All right. Who remembers how to use this function? Let's see. Names, pivot. Oh, pivot longer is what I'm looking for. Let's see. Poop. Names two. Right. Let's see. Oops. This one always trips me up. Let's see. Calls. There we go. Okay, so now that's in long format. So I have basically the metabolic parameter in one column and then the values in the next. And this would allow us to make a nice plot in ggplot of all three together. So if I go use date, time, stamp on the x-axis, y is going to be the values, color is going to be defined by the name of the parameter. And we should be able to just do like so. So remember these are instantaneous values. So it looks kind of weird, but we have NEM as the difference between P minus R. So really it's just shifting that P curve down by that R constant to account for it. Now you might ask the question, is this an autotrophic or heterotrophic system? We can also do that, unfortunately, manually, and this will be included in a new version. We can just take the average of the parameters by day. So before I do that, I gotta make the date. Okay, because this is a date time object. I want to average by date instead of date time. Let's see, value going to be the mean of the value. Always a good idea. Do the NARM equals true. And it's going to be averaged by date and name. So I don't want to average everything together. So now we should have daily estimates of everything, which we do. So now we can plot this again, but using the new plot object. And then I gotta say date instead of date time. There we go. So this example this week, or actually, let me make R negative so it's a little more clear what's going on. Let's see. Because oftentimes R respiration is expressed as a negative value to imply that it's subtracted from production, especially on plots. So let's just do that for visual comparison. So here's negative R down here, here's production up here, and here's NEM as the difference between the two. So you can see the system is somewhat autotrophic. The first couple of days bounces around and then sort of goes back towards heterotrophic as production seems to lapse a little bit. Great. Well, what do we do with that information? That will be in the next discussion. I'm just trying to demonstrate you how you would get that information from the results. So that's really all it is to running that model. So you give it the data input, you give it the time interval, you give it the depth, and you can just basically look at the results plotting several different pieces of that, either using the functions within EBASE or on your own. All right. Now, the next thing you might want to do is, well, now that I've got the results, how do I make sure they're not bogus? Because after all, this is just an estimation process. There are a couple ways to do that. They're all fairly easy. But first of all, I want to show you again what's in the model output. So says fit, we look at the model output. You have these, there's this R squared column and there's converge column. The converge column basically tells you whether or not the MC iterations converge towards a stable solution. So did they get an estimate that was consistent across multiple simulations? It will say, I forget what it says. It will say something other than fine if it didn't converge. So let's look at a table of those. I'm just going to look at date and converge. The table function is super convenient for just tabulating results. So this comes with base R, but basically, if you say, I'm going to look at these two columns only and give me the unique combinations of values in those. So right here we have all of the dates and all of the instances that fell in that converge column. So every single one of those dates, the model converged. And this fine value is repeated across rows for every group or every day, because it just only applies to one model per time, per period within which it was estimated by that grouping variable. So that's good. That just says the model reached a stable solution, but how good are those solutions? Well, one way to look at it is how well was dissolved oxygen even modeled. So we have R squared values, and basically we would like the modeled DO to look pretty similar to the observed DO. So we can look at the R squared values similarly. I'm just going to do the unique values now. So RSQ for R squared, that's just looking at the unique values for that column. So basically it ranges from 4%, which is atrocious, to 62% explained variance for that R squared value, which is pretty good. So you get across the board, and just because you get low R squared doesn't mean the model is necessarily bad. It just brings into question the actual DO data for that time period. Because remember, like, all open water methods are based on that diel curve throughout the day. So as the sun comes up, production starts happening, DO will start increasing, it'll reach a peak late afternoon, and then as the sun goes down, less PAR availability, respiration starts to dominate the process, and you start seeing DO go down, and it continues to go down until like early morning, right before the sun rises. If a DO time series does not have that clear signal, it's very hard for the model to fit parameters to it, because the entire assumption is that it is following that cycle. That's true for EBASE. That's also true for Odom's method. So how do we look at that? We have another function called fitplot, which we can use to evaluate our model. So this is showing you the DO for that 1 week period in the points, the observed values, and the model DO that EBASE created when it was trying to fit it to the metabolic parameters. So, the fitted data do have that nice diel curve, and that's mostly because it's driven a lot by PAR. PAR has a very clear increase, decrease, as well as other things like, how respiration plays into it. Now, I think it was the, fourth day right here that had the lowest R squared. Well, look at the observed DO. It's like highest at 3 a.m., lowest at sunrise, highest at 3 p.m., or high again at 3 p.m., and then finally low around midnight. This is not a clean diel signal of DO, so the fit of the estimated model DO to that group of observations is going to be terrible. So all this is telling me is that the DO data is super janky in that optimization period. The other thing to note here is that you get one curve per day. That is because, like I said, the model is run 1 day at a time. So you don't get continuous DO estimates throughout the period of that you're modeling, unless you tell it to apply one model to the entire time series. And there's pros and cons of either approach we'll talk about. But this is just to show you how the model works in terms of when it's estimating the parameters and how they are created in the output. So like I said, one estimate for R, one estimate for A, one estimate for B, each time the model is fit. So you just get that value changing one day at a time. There's other ways to display this. We could do it by group. That's actually the default behavior. So this breaks it out by each optimization period for that model. So group 1 is the first day, group 2 is the second day, and it shows the corresponding R squared at the top. So that's just another way to really diagnose when the DO observations are not particularly useful for estimating metabolism. So that's one thing you do. So again, you could look at the converged statistic, the R squared statistics, and then plot the model data against observed DO. The last thing is a plot of the credible intervals for the estimated parameters for EBASE. Let's go back to R, and all you got to do is just type credible plot, put in the data, or put in the model results, and you're good to go. So remember, these are the parameters that EBASE estimates: A, R, and B. A is used for production, R is just respiration, and B is used in gas exchange. These credible intervals give you an idea of how likely those values are, given the data and the prior information you've supplied to it through the priors. So this point is going to be the estimate you get on any given optimization period. And then the whiskers around that is the credible interval, like I said, which is like a confidence interval in a Bayesian setting. So what we're looking for here, oh, this is janky because I made R negative, but this should be right in the middle over there. Normally it doesn't do that. So that's because I manipulated the data. Let's try that again. There you go. Okay. I think I'm still sort of wondering how best to interpret this information relative to the priors. But what you're looking for, I think, is a pretty narrow credible interval relative to the priors that you've given it. And I could probably provide an overlay plot that could give a more useful comparison here. But if you look, for example, this B parameter, if you remember the prior plot for that one is centered around 0.251. That's a value that is from that Wanenkoff paper that we took the gas exchange model from. But we've allowed it to vary between 0 and 0.5, given instabilities in the model that were observed if we didn't constrain it to an upper value of 0.5. The other priors don't have that upper limit on the constraint, but we had to constrain that one. Now, how that relates to the credible plot, let's see, where's my plot? You'll see that the credible interval pretty much encompasses that entire prior distribution, meaning these estimates don't really tell you anything. They could be anywhere from 0 to 0.5, even though they're centered at 0.251. This has been a problem with EBASE that we don't yet know how to solve. The B parameter is not super constrained very well, given the data that we've used on the model, and we've looked at several locations. But there's a workaround for that. You don't have to estimate that parameter. You can give it a value as your prior information of it's going to be this value. And so that's just one way to get around this issue. But all that is to say, I'm just giving you context for how to interpret this credible interval plot relative to the priors, and to also show you that the B parameter is one that is sometimes problematic. And okay, and then lastly, you got credible prep, which is another convenience function. If you just want those values as a data frame, that's available to you. Yeah, so that's kind of a lot. I've been talking for about an hour now. I'm going to pause for a second. Does anybody have any questions about this? This is all super obvious and intuitive. There's Harry. Yeah.
So for in your paper, right, your 2024 paper, you just set the B value as the value given from Winikoff, right? Do you have in a literature review, have you done it in terms of trying to figure out values that could be more applicable to estuarine system, like an estuarine system as opposed to open ocean?
Well, that's the thing. There's not really anything in the literature that describes that, so we don't know. That's why we
Yeah.
picked 251. That was the only one. We were hoping that, you know, how Bayesian models are meant to work, you present it with some data, it might be a means to constrain that estimate for B, you know, because it's going to give you the most likely value given the data it's presented. But consistently, we just saw these intervals that were quite large, meaning that there's really not a whole lot of capacity to accurately estimate that parameter. And if that is the case, it's better to just fix that to a value that's informed by the literature, which is what we did for most of the paper and is probably something you all should consider when you're actually using this model in practice.
But aren't there like other ways you can estimate gas exchange rate? Like you can look at like at nighttime, like the rate of like O2 depletion, and then somehow try to tie that to gas exchange, or like I don't know, other ways you can. I mean, yeah.
Yeah, I mean, there's a lot of different ways you can model it. The if anybody was on the last training we did with the ODM open water method, that uses a formulation from a 2008 paper that is, I forget what parameters drive it, but it's different from the Wenenkov model, which is basically a wind-driven approach. So you can model it any way you want. I mean, I would obviously defer to the past literature, but it really depends on what you think is driving it, or what assumptions you want to make of which part of the DO time series you could, you know, slice and dice to say, oh, the remainder is gas exchange. Um, there's in the ODA method that we have in that weight reg DO R package that I used for the last training, there's an option to use Weinenkov and that other method, the original one from Thibault et al. 2008, I think, or something. Um, so yeah, but EBASE is hard coded to the Weinenkov. If you really want, you can download or you can feed it a custom model file. There's a way to do that. So basically, the way JAGS, how that model works, you give it a text file that's written in JAGS, which is looks a lot like R, but it's a little different, and it specifies that core model. So that one, basically this,
Mm-hmm.
and you could change it to, you know, have gas exchange calculated differently. You have that ability, but that might cause some further issues downstream in the package with reading in the model output, but it's possible. And I'm never, you know, closed to making changes if people think they're worthwhile. If there's some other way to do it, we could work that up and see if we get, you know, improved results. So long answer, but yeah.
No, thank you.
Stephen, you see, can we tweak the number of iterations? We did not test a nut sampler like Stan. No, You can tweak the number of iterations. There is an argument in EBASE for doing so. Let's see. The number of iterations by default is 10,000, and that's basically the number of Monte Carlo stochastic samplings it does. This is an excessively high number that I think is going to be sufficient most of the time. If you want the model to run quicker, you can probably drop those down to 5,000 and still be okay. Same thing with the number of chains. This is like this is where I get a little unclear what this is actually doing, but this is the number of Monte Carlo chains it's actually running and together at the same time. And so you could actually, ideally, I think this number should be a little bit higher, but you can also reduce or increase the processing time by increasing this number, reducing or increasing this number. It's really a trade-off between having the model converge, giving it enough freedom to converge versus how long you want it to run. So, but we didn't use Stan. The original stream method used JAGs as well. So we basically started just by deconstructing that model and rebuilding it with parameterizations that we thought were appropriate for estuaries. Okay. A few more things, then we're pretty much done. Let's see, okay. So on the topic of runtime, having metabolism for a few days is probably not all that useful. And, I often think about metabolism on seasonal scales. So the example that I was showing was really just a shorter time period to increase, or rather decrease model runtime. In practice, you will want to do this in parallel. In other words, using multiple processors on your computer. By default, R doesn't leverage this. You have to set it up specifically. It's pretty easy to do. There's this do parallel package, which you did install for the workshop. You'd want to load that package, identify the number of cores you want it to run on, and think of it like, you're running, it's just like in engineering, you have running batteries in sequence or parallel or something like that. If you don't do things in parallel, it's going to just run from day one all the way to the end of the time series. Doing it in parallel will cut it up into chunks and send each one of those chunks to a different processor. So they're all running at the same time, just on different parts of your machine's hardware. So first of all, you want to tell it how many processors or cores or threads or whatever you want to run in parallel. And there's this nice function in do parallel called detect cores that will show you how many you have available to you. Don't use all of them. Your computer will come very hot and probably you won't be able to do anything until it's done. So it's good to say, what is the max number of cores, and then subtract 2 or even 3. Then you say, this is the number of cores I want to use. You create the cluster. This, I don't know what it's doing under the hood, but makes the cluster based on the defined cores. You set up a backend, and then you just run EBASE as before. And then when it's done, you want to shut it down, basically stop the parallel setup, just close it. I don't know what it's doing, but that's just what the package says. For short examples like this 1 week we're looking at, this will actually probably run slower because there is some computational overhead to setting up the processors. It's trivial, but point is, like, if you were to run this on the 7 days we just looked at, you'd be like, oh, it takes just the same amount of time. This has proved not useful. That's cool. You don't do this on short time series because the time it takes to set up the processors is gonna negate any gain you get in processing time. Where it comes into play is, say you're running it on a year of data. So Lindsay said, she did 1 year of hourly steps on her computer in 25 minutes. You could probably cut that down to 5 minutes by running this in parallel. So there are examples in the help files that have this, also literally right here on the website. But anytime I'm running it on more than a month of data, I'm doing it in parallel. The other thing, and I just realized yesterday that the version of EBASE on CRAN does not have this function. So I will push that up there soon. But if you want to, for example, download 25 years of swamp data at a site and run EBASE, this will take probably about 24 hours, but you can do it. I kind of envisioned that folks on this call would want to do something like that. Now, I tried that using this approach, and the model would just randomly crash somewhere in the middle of the time series. I have no idea why it was doing that. But I thought, okay, well, I can just set it up in a way where it runs 1 year at a time and then stitches the pieces back together. And if it fails on a particular year, it will restart and try to fit it again. And you can define how many times it tries to restart. But this I would run on many years of data because, again, if you weren't using this, you'd have to start from the beginning, and it's just hours of wasted time. Because it will fail just randomly. I don't know why. It doesn't happen a lot, but it happened enough. I needed to create this function, or it will simply fail because it's missing a huge chunk of data, like a hurricane came through, and that's totally fine. But you don't want the computation to stop there. So this does run in parallel. You don't need to set up the backend like you do for this, but you do have to identify the number of cores you want. And when I ran this, I think it took about 18 hours or so, but this is like, I think the full record at Drybar. Yeah. So just those are some examples of how you might want to do this in the real world. Okay. Now, the equation optimization length, which sounds scary, but like I said, it's just that period of time within your bigger time series where the model is optimized or fit. You can change that. There's an n days argument in EBASE where the default is 1 day. So the number of days for optimizing is 1 day. But you can change that to 7 days. So, or 2 days or 3 days, whatever you want. So let's just do that. I'm just going to copy existing n days 7. Take a few seconds to run. I got those same warning messages. That's fine. I was already expecting that. But if I plotted the data, you can see how it differs. So let's just look EBASE plot. Oops, that's showing you the results. Now, this is, again, production, respiration, gas exchange. Respiration is constant across the time series or the optimization period. That's to be expected. That's how the model works. It's not a unique estimate at each time step. Same for A, same for B. The reason these look continuous is because these vary as a function of wind speed, salinity, water temperature, PAR, but there is only one estimate for A, R, and B in this entire 7 days. And we can verify that by the credible plot. So those are our single estimates. Now, why would you do that? Why would you want one estimate for A, R, and B for that entire time period? It really depends on your question. I think if you're just using a week of data, using 1 day for the optimization period is fine if that's all you have. But if your question is, how is metabolism changing throughout the year? I would probably prefer a 7 day, maybe even a 30-day optimization period. Because I don't care about what respiration is on any particular day. That's not the temporal scale of interest I'm concerned with. I want to know, how is it changing seasonally or monthly? And if that is my question, it seems like it makes more sense to me when I'm optimizing the model to give it enough data to be able to accurately estimate the parameters. So it's this trade-off between the data that the model is exposed to and your question of interest. So I would want to use a little more data if I'm looking at longer time periods. But if I was looking at a shorter time period, 1 day is okay. And it's also, the scale at which you think processes are affecting metabolism. That example I showed earlier in Tampa Bay of the red tide, that was, a 2-week event. So maybe 2 days as the optimization period might be okay, or 1 day. But again, looking at a year, I'd use a bigger window. It's really up to you. So that's the most solid guidance I can give on that. We did in the paper, we did a sensitivity analysis of how well EBASE was at estimating known parameters from simulated data. And basically, if you give the model a longer optimization period, it will eventually converge towards the true value. But how practical is that for understanding, whatever your question is, if you want to look at processes like weather events that happen on a weekly scale or something like that, if you're using 30 days as the optimization period. So it's up to you, but just know that you can change it. Yeah, so here's the fit plot for that same model. You'll see that there's a continuous DO modeled throughout that cycle. And I would say this is, just looking at this isn't great. It's missing a huge peak here. It's missing some dips, down here. So I would look at this and say, oh, and this is pretty bad right here too. So this is a signal to me that 7 days is not a good fit for this model. Yeah. So change that, but also consider what your question is. All right. So I'm totally blasting over the exercises here. Is everyone still okay doing that, or do we need to take a break, or how's everybody feeling? Thumbs up if you're good to keep pushing along. All right. We've only got 2 sections left. Given that I said I was going to finish this one at 1:30, I'll try to do that. But I did want to talk a little bit more about what happens when you have missing data. In that other example for the 3 years at Dry Bar, we had a huge gap after Hurricane Michael came through, but there were a few other smaller gaps that could have been from, instrument out for maintenance or something like that. How does EBASE handle that? So I'm going to just show you an example of when the model retains or excludes missing data. So I'll just copy this because I don't remember the index numbers, but it's a picture of my cat. Let's see. So I'm going to take that subset data, that 7 days APA DB sub. I'm just going to pull out a couple observations. What this equates to is a couple hours. This is just based on the index, and I'm doing it for dissolved oxygen. This is a couple hours. This is a whole day. So if I were to just do that, and I wanted to plot, this is just simple base R. That's the whole thing. This. Yeah, so this was, I think, right. So this was the time series we just estimated metabolism. This gap, I think, was already there. This one I put in there just for this example, and this is also one I put in there to remove that whole day. Now, when you feed this data set to EBASE, it will interpolate all of these gaps. Because, like I said, the JAGS model, the MCMC model, will not work if there's any missing data. So we need to fill those values in. And just to show you, APA, yes, Z, what do I need to put in Z? Okay. This is actually used inside of EBASE, so I think it requires all of those. 600. There we go. Okay, so you can see a nice plot of like, oh, okay, this is interpolated, this is interpolated, this is interpolated. And like I said, it's a linear interpolation, so just connecting the dots. Obviously, so this is March 11th right here. This is going to give you garbage metabolism estimate because one, it's not real data, and two, it doesn't look anything at all like a DO signal you would expect. This one might be okay because you have most of the day, and it's really just connecting the part of the DO cycle that is increasing DO after the sunrise. So you might want to retain that. If we were to run EBASE on this outcome, or this time series, we can see what happens with the output interval. So it's running on the missing data. I want to set up the EBASE plot. Okay, same warnings. That's what we expect. And then, okay. So you'll see that there's no results for this whole day. There are results for the gap that was interpolated here, as well as the one that was already in the data right around here. This is the default behavior for filling missing information in EBASE. It will, by default, only keep output that has interpolated values less than, I believe, 12 hours. What did I write? Yeah, 12 hours. And that's with the idea that, yeah, if there's less than 12 hours missing in a day, you might still describe a reasonable approximation of the diel cycle for dissolved oxygen in that period. If you're not comfortable with that, you can change that. There's an argument in EBASE for defining that maximum distance that the data are thrown out. EBASE. It is the max interp argument. It's basically a number that says the minimum number of continuous observations that must be interpolated within a group, defined by n days to assign as NA and output. So how is that determined? If you have a 60-hour time step or 60-minute time step and let's see, max interp divided by interval. So my interval for this one was 3,600. It divides your interval by number of days, number of seconds in a day. Is that right? 60 something, yeah, I forget. Whatever. This comes out to 12, so 12 hours. It converts your whatever your interval is to hours, and so by default this is 12. So if you wanted 24, you would just say 24. So that's it. So you can change that. This is something that the original base method never had. So this kind of works out of the box with missing data, but it's up to you to, make sure that what is returned is okay. All right, so the last thing, and I promise this is the last thing, we want to talk about how to change the prior distributions if we have reason to do so. And remember, the default priors are informed in the sense that we kind of took them from the literature based on averages and spread around that from Caffrey's data. But they're still relatively uninformed because they do describe a pretty large range of values. If you remember in EBASE, if you go back to R, looking at the help file, it's already up. These are how the priors are defined. So for each one, A, R, and B, you have the mean and the standard deviation. And these are truncated after the fact to greater than 0. And then the B is also truncated to not exceed 0.502, so twice the mean. You could change all this, but if you wanted to say, oh, I want to fix the B prior to 0.251, you cannot say 0.251. You have to give it a standard deviation as well. You basically give it a very, very small standard deviation because the JAGS model needs something to work with. That is a distribution, but it's still a very small distribution. So let me just first demonstrate this with the prior plot. So if you wanted to change B, still keep the same mean, but more or less fix it at that value, you could do standard deviation of 0.00001 or whatever that turns out to be. If we were to plot that, the prior, you'll see that the curves look more or less the same, but if you look at the range of values for the B prior, it's pretty much 0.251. For all intents and purposes, this is 0.251. If that was to translate to the EBASE model, you would just do this exact same thing. So I'm going to copy this. B prior, so C is over 2, 1, and E to the -6. Fit that, and then in your credible plot at the end, you will see that the estimate is pretty much 0.251. And why would you do this? Again, one, you might already have an empirical measurement of this value from, in situ data or something like that, or some estimate from some other approach. Or you just know that maybe this parameter is not stable in its estimation. The credible intervals are large. So when we do constrain it, you'll see that, yeah, it's still pretty, wide, but it's within 0.251 because we told it to do that. These other ones, I might trust a little bit more because now this is no longer a free parameter, and we can maybe, these can be better estimated from the data. Or not, if this is wrong. We don't know. But if you have, yeah, there's a lot you can do with these methods. And I like it because you can let the model do its thing or constrain the model yourself. You can't do that with more conventional approaches to doing these things. And that's it. That's all we got. How's everybody feeling? Are we done? Do we want to take a break and then just go through some examples? I'm up for whatever. I'm happy to give you an hour and a half back. Or we can just, because I'm just going to keep coding up here. It's up to y'all. Let me know in the chat what your preference is. Take a break or call it or keep going. Okay. Well, let's take a 5-minute break. Then I'll show you one example. You're very welcome, Theo. But yeah, I would like to show you, and if Ethan actually can hang on, this will be another Apalachicola example that he can explain a little bit more about. But yeah, let's take 5 minutes, and then we'll reconvene at 1:30. We'll call it 38. How about that? All right. It was 1:39. I gave you an extra minute. I have two examples here. I think Piney Point one is an interesting event, but as far as the examples go for this workshop, I think the Apalachicola intersite comparisons are a little more interesting. So I'm going to do those and probably call on Ethan's expertise to provide some additional context here. As far as setup for this, it's literally everything we went through in the second lesson. You use Swamper to import the data. You filter QA/QC flags. You reassign and select columns of interest, convert par to the correct units, and do this for more than one water quality station. Now, in the future, I was thinking this, if this group has a need for it, all of this nonsense right here could be incorporated directly into EBASE. So basically, all you would have to do is specify where the files are and which stations you want to combine. If that would be helpful, I can include it, but I won't know this unless somebody tells me. Otherwise, I won't do it. Because this is the steps to do this are kind of tedious. Let's see, Apalachicola example. But I'm just going to copy paste from there. Okay, so there's the weather data. Let's see. Just for fun, I'm going to show you that you can get the import function will tell you what it's doing is it's importing the data. If you change this argument to true, so it just imported 3 files. It's done. So then we clean up. Then we do the same thing for dry bar water quality. We clean up the QA/QC flags. We combine it with the weather data, 60-minute time step using a union. And then we select the columns we want in transform par, convert par. Let's see. So we do the same thing for the East Bay water quality station. I've imported the Met data twice, but that's fine. So you just run that, and then we'll have 2 files that we can use for EBASE. So that should be the same one you had from earlier. And here's East Bay. Let's plot the data. Let's see what it looks like. So we got Plotly, APADB, X, date, time, stamp, Y, VO obs, type equals scatter, mode equals lines. Do the same thing. Oops, for East Bay data. And just to remind y'all that both of these data sets use the same weather data because there's only one that's relevant for these two, and it is at East Bay. So dry bar uses the East Bay Met station. All right, I'm going to show you a neat little trick with Plotly. Excuse me. You can create 2 plots together using subplot. But I don't want them side by side. So what is it? N call, N rows 2. There you go. All right, so see, there is a way to link the two together. Share X. Let's see if that works. I was having issues with this the other day. There we go. So yeah, now you can they'll scroll together. Oops, I keep doing that. No, looking for this one. So you can sort of see how DO may or may not, be in concordance between the two sites. I would not expect them to, because these are very different locations. But also look at the magnitude of the DO. So dry bars at the top, East Bay is at the bottom. You get a ton of looks like hypoxic conditions in East Bay. Because it's near the river outflow. It's kind of got a lot of organic accumulation, organic muck accumulation. So a lot of decomposition of organic matter, a lot of respiration. And then dry bar is more open estuary. So this DO time series, just by looking at it by itself, tells you a lot of information. Let's see. So John had a question about using import local with non-swamp data. Yes, you have to cheat. You can. I have an example for that. You basically have to rename your data file a station name for a swamp parameter that it recognizes, and pretend like that's data from that location. And I would pick a time zone that applies to where those data are from. It's kind of annoying. I wish there was a better way to read in non-swamp data. John, does that make sense?
Yeah, I think so. It's just another site that we have at in Elkhorn, but it's just a non-swamp site. It's a restoration that we did, so it'd be really cool to do this work on pre-restoration and post-restoration.
Yeah, absolutely. Yeah, I would just name it one of the water quality sites at Elkhorn and import it that way.
Okay.
Because
Perfect.
Swamper has a lookup table of stations and time zones and lat long. And if it doesn't, if
Fit
there's an
those.
incorrect station entry in the code for station code or whatever it is, it'll tell you, I don't know what this is. So you got to trick it and say like, oh yeah, this is from
Okay.
a place that exists.
Oh, this is our site, but it's not.
Yeah.
Right.
And then you have access to, once you get it in there, you could use QA/QC, no problem. And then, you're good to go. It doesn't have to be a Swamper data object once it's imported into R.
Yeah. Yeah. Perfect. Yeah, I remember trying it before and it would just not bring it in, but I had it a different name.
Yeah.
Yeah.
I've had multiple people ask me that.
Yeah. Okay.
So I guess that means I should probably formally include it somewhere anyway.
Okay,
All
thanks.
right. So we got the data. So East Bay dry bar. Oops. Let's just look at the dimensions, or the dimensions. So 3 years of data. Now this next part, I did something for you. I actually ran EBASE on these 3 years of data. And it took a couple hours, but I saved this information in the zipped data file that you downloaded for the workshop. I said you did not have to unzip it, and that's true if you're just pulling in the swamp data. But if you want these two files, you have to unzip it and then import them because these are not, CDMO files. So you cannot read them in from a zipped folder unless you want to do some extra work in R. So once you unzip them, you can just load them like any other R data set. And if you unzip them, make sure the path to the unzipped folder is correct. It very likely is not going to, it's going to be data 36727 slash 367272 slash however, how, unzipping things work. It creates like weird duplicate folders. But anyway, once the path is correct, you can load it. So these aren't particularly large files. It just takes a long time to run EBASE. But we have for both of these full results from the model output. So let's look at some plots. And this one, I have no interest in seeing the instantaneous rates at every 60 minutes because it's 3 years of data. So I'm going to do the daily averages, which still looks absolutely insane. So how useful is this? Not very useful. Now we're kind of getting into the utility of metabolic estimates and what you might do with them. This tells me absolutely nothing. And there's, I think, yeah, the post Michael data is already gone in this. But I think what you should do next is then look up, the convergence and fit metrics, but I'm going to skip that to something a little more interesting. You can go through that here. Basically, I'm looking at the convergence metrics, R squared values, and in this case, looking at the days with the 10 lowest R squared values. Actually, that is kind of cool. I'm going to show you that one because you can see there's a stark difference between when the model fits DO good and when it fits it poorly. So these are the top 10 lowest fits. And DO observed is all over the place. So I'm not surprised the estimated is not a good fit. And these are not truly zero. It's just that the label rounds the R squareds. So let's look at the top 10. And you'll see what I mean. Freaking beautiful. Look at that. You get a nice observed DO, nice fit. That's what I love to see when I look at DO data. So yeah, it's good to just look at it when you have, 900 some odd or 1,000 days over 3 years. It's not practical to look at everything, but it is useful to look at the bookends of the best to the worst to get a sense of really, is your DO data telling you anything useful? Because, most of the time it doesn't, not most of the time, often it doesn't follow that nice diel signal. That could be from the tide. Could be that there's not a lot of production there. And that's fine, the model will do what it can. But yeah. Okay. What am I doing here? Okay. So the point is I wanted to compare and contrast these two stations based on what I know, and I'm sure what Ethan can describe relative to how these locations differ. Again, East Bay is kind of at the mouth of the river, a lot of organic muck accumulation, lots of hypoxia. Dry bar is more on the open estuary, less riverine influence, more tidal flushing. And I would expect that to affect metabolism in terms of autotrophy, heterotrophy, whatever. So, what am I doing here? Let's see, weather data. Okay, so this code is going to like parse out and combine the metabolism data from the two stations. So I am going to do this. So I type it out. Oops. Okay, so I think we want to pull out the weather data. See, oh, I kept wind speed. What am I doing here? Oh, I know why. Okay. So I want to summarize this by daily averages. So I have to separate the PAR from salinity or metabolism data from oh man, it's late in the day. Okay. I want measures of the physical properties in the system as a means to explain metabolism. So I'm starting with dry bar. Let's just I don't think I did this right. All right, whatever. This is 2017 data. Oops, because I know that was a year where it was decent information. So we have averages of PAR, salinity, temperature, and wind speed. I'll tell you what. I think I did this wrong in the example. Is PAR, salinity, and temperature. Let's call this physical. APA DB physical. I want to do the same thing for East Bay. Okay. APA EB. See, I don't want wind speed because it's going to be the same between the two. Let's see, mutate. I'm going to call this site APA EB. Site. Oops. APA DB. Okay. So what I'm getting towards here is I want to isolate again the physical and well, the physical data as a means to explain the metabolism data. So I have to pull that out separately from the original input data, separately for East Bay and Dry Bar. And then, yeah, so I'm going to pivot these a bit longer. Minus date minus height. Oh, minus date. All right, cool. I really hate that function. I can never remember what the heck the call. Okay, now it's in long format. APA EB. Why? And we could do the same thing for dry bar. So here's the physical for dry bar. I want to do wind speed as well. Actually, you know what? I'm going to keep wind speed in this one too, for sake of comparison or combining the data. Then that should work. Okay, and then awesome. Awesome. Okay. Physical data. Let's see. We'll just combine these two. Find rows, APA, dry bar, physical, APA, East Bay, physical. And then we have the physical data in long format for the two stations. So we can start comparing it with metabolism data. So I'm going to cheat now and use my code. So here I'm combining the metabolism because I'm pretty sure you guys don't want to see me just work through an example like this in real time. This looks super complicated, but it really is not that bad. All this is doing is combining the data sets, the results, using an identifier for the station. So this has both dry bar and East Bay. That's first done by creating a list with the names, condensing it, and then unnesting it. So this is a very convenient workflow for combining list elements. So this blows out the value column. Now they're combined. This is a whole other course in like dplyr and tidyr, but just trying to demonstrate what's being done here. Then I'm creating a year variable, or I'm filtering it by year 2017. I'm selecting the metabolic parameters of interest. I'm calculating NEM, and I'm taking the daily averages. And it should be much simpler when it's there. So we got A, B, NEM, R, and P, the things we want. Now I can join that to my physical data, I think. Almost. Let's see. Yeah, I don't actually want that in long format, so I will recreate that. Okay, so I just recreated the physical data in wide format, where we have basically variables across columns as opposed to variables within rows, and then the site designation. Because I want to join this to the combined data, and actually I want to rename APA-EB. Okay, that's fine. Oh, that's not fine. So I want to join by date and site, I believe. Let's see, date, site. Yep, that's what I want to do. Let's see. Name. Let's see. I want to call this site. Site. That should work. Yeah, okay. So you probably get the impression then that a lot of data analysis is just munging up data, which I'm sure you all know. But now we have a nice data set where I've combined the daily metabolic estimates from two locations We've got A, B, NEM, R, P, and match them up with daily estimates for their corresponding physical data, PAR, salinity, wind speed, and water temperature. Why are we doing this? Because I want to know what's driving NEM. Is it temperature? Is it PAR? Is it something else? There are many other variables you could include in this data set, like nutrients. I specifically did not include that example because nutrients are a whole other beast because they're not continuous. And you would have to aggregate at a monthly scale pretty much, which is not a problem. It's just a lot of extra steps in between to get to a data set like this. I still think these comparisons are useful with some of the examples that I've got. So I haven't saved this in a while. So you guys, if you're using the live coding, there it is. Let's make some plots. Let me just see how NEM changes between the two sites. Use ggplot. APA combined is the data set I've got. I'm going to use date as my x-axis, use NEM as my y-axis, and I'm just going to do a line plot with points on top of the lines, and then make two facets by site, put them in one column. See what that looks like. Cool. Okay. On second thought, I am going to remove the points and put in a horizontal line at 0. Y-intercept 0, color it red so we can see it. And now, see what that looks like. A little more interpretable. Okay. Does anybody want to take a guess as to what is going on here? What is so different about these two sites? Or if Ethan wants to chime in, I welcome his interpretation. Steven says seasonal hypoxia in East Bay. I'd say that is what's going on. What about in the context of autotrophy versus heterotrophy? Dry bar seems pretty balanced, right? It's, even looks more autotrophic at times, like in the spring, which, would make sense. That's the beginning of the growing season. East Bay, for the most part, is more heterotrophic, particularly in the summer. So there's not a huge, but the consumption of organic matter is much higher than the production of organic matter, which is consistent with hypoxia. Decomposition consumes a lot of oxygen, and decomposition of organic matter. So I thought this was a pretty stark example, or linked to higher river flow, correct? I did actually make a plot of salinity, I think, versus NEM somewhere. It wasn't particularly telling, but yes, this is a lot more riverine influenced as well. Not exactly sure how that plays into it, but just based on the knowledge that these are in two very different locations, and NEM reflects that, I think is pretty telling. Let's see, we can also do a one-to-one comparison. So let's select site, date, NEM, pivot, wider names from site values from NEM. So I want to compare the two directly now, rather than just plot them on separate facets by date. So now I've kind of got it in wide format again, and now each column is NEM by the two sites. So just for fun, let's just see how they correspond. To plot. I'm going to create a 1-to-1 line. AB line, slope equals 1, intercept equals 0, and then a linear regression method equals LM. No standard error, I don't care about that. And then we're going to color it red. Oops, got my points. What does that tell us? Okay. Respiration is higher at dry bar more often than not. I'm not sure that's particularly interesting. That's in my mind, I don't get anything from that plot that I don't get from this one. So not that great. Okay, now I do want to, now that I've painstakingly gone through and combined the metabolism data with the physical data, I want to just look at some comparisons of the two to see what might be influencing metabolism. So let's look at the B parameter. X is going to be wind speed. So remember that B parameter is going to be kind of like a measure of how sensitive metabolism is to changes in wind. The idea being that more wind there is, the more turbulence is going to be at that air-sea interface, and you're likely to see more gas exchange. So you might expect that B parameter to be higher on periods when it's more windy. And you might expect the parameters overall to be higher at dry bar because I believe it's more open water. I'm going to steal this. I hate that default theme, so I'm going to do black and white theme and site and call equals 1. Interesting. I am not going to do that. Instead, we're going to color it by site. See if that's not something absolutely terrible. Okay, so this makes sense, right? So as wind speed goes up, and remember, this is a model that's optimized daily. So you get one estimate of B for each day. So on windy days, the B parameter is estimated at a higher value because the wind is influencing gas exchange. So when you look at on windy days, a DO time series, that the values in that time series on windy days are going to be influenced by flux from the atmosphere a lot more. And obviously, as wind speed increases, you see that positive slope. That's literally what I just explained. And overall, the values at dry bar are higher because this is a more open water site that's more wind influenced as opposed to East Bay. So this makes perfect sense to me. How this would apply at other reserves, you could do the similar type of analysis of two sites where one's more open water, where another one might be more back bay, and I bet you'll see more or less the same thing. Um, okay, some other interesting ones. I think, let's see. Oh yeah, let's look at par and production. Just gonna copy this. Here's par in watts per meter squared. Production. See what this looks like. What does this tell me? Well, there's a freaking outlier. Which one is that? Let's see, par is crazy high on some day. Let's remove that. Find out what day that is, first of all. That is going to be July 24th. Here, I'll just remove it this way. So T43, I will filter out that max value. So filter R not equal to, or actually max R. So if I ran this right now, it would just get me the observations where par is max, right? So I want to just put a negation right there, exclamation point, that basically flips that true false statement to give me everything that's not at the maximum par. So that's good. Now, if you were to plot that, those outliers would be gone. Still not super interesting. I mean, in a way, this does kind of tell me that production is more sensitive to par at the dry bar site when it's dark. There's not really any production that follows, first principles of metabolism. East Bay, I don't know. That's kind of weird. That could be an artifact of the model in East Bay not fitting as well because you get a lot of hypoxia, and that could be driving that relationship to being fairly flat because there's not a good diel signal. That would be my guess. There's more you could do to explore that hypothesis, but that would be what I think is happening there. Let's see, and what else? It's another good one. Temperature and respiration, maybe that's interesting. Site. So why would you think respiration is driven by temperature? Well, there's no explicit association of temperature with respiration in the EBASE model. The original base model, I believe, had a temperature component in there. We decided to not include that because respiration is not, we justified it as not as tightly coupled to temperature as it is in streams. So we didn't include it in there, but I would still expect temperature to be related to these parameters as opposed to coupled through a model equation. So this makes sense. Warmer temperatures, more bacterial activity or decomposition happening. And again, I think that lack of a slope at East Bay does relate more to just a muted DO signal overall. So it's a reflection of maybe poor model fit, as well as just, I don't know, just a heterotrophic system that tends to just be decomposing more. Let's see, one more maybe, and then I'm going to call it. Let's see. Salinity, maybe that's interesting. Salinity in NEM. Oops. Let's see, not that interesting. I guess I was maybe expecting that salinity at East Bay might be more associated with NEM because it's a more riverine influenced site, and NEM might be driven by river pulses, and that could be reflected in salinity. But I'm not seeing much here. Really, this is just, the shift in the intercept for these that tells me that dry bar is more marine influence because it's got actually no, never mind. I'm NEM, the shift in NEM. NEM is not as low at dry bar. But yeah, you do see overall lower salinities at East Bay. There are times when it looks like it's bumping up against zero, whereas dry bar, the lowest one in this data set, at least on a daily average, is slightly above 5. So you can kind of make statements about how the ocean influences these sites, but not that interesting for metabolism.
Marcus, what happens if you plot respiration against salinity?
Let's find out. Not much. Just higher respiration at East Bay. Yeah. So, I mean, these aren't super interesting examples, but I guess I'm just trying to give everyone a sense of how you might start exploring what's driving metabolism. And you could even, there's a clear temporal signal in these data. You could do assessments by season pretty easily. That's when you do see large differences in NEM. Whereas in the winter, they might be more balanced, and that is probably a function of temperature, seasonal temperature changes. Inter-site comparisons between reserves, not just sites within a reserve. There's a lot of interest in that, because metabolic signals are going to be a lot more pronounced across latitudinal gradients, where you have just changes in climate driving these things. So, I hope I've kind of planted a seed of how you might use these data. Hopefully, you are inspired or you're just very tired like me. But yeah, I think unless you guys want me to keep just coding, I think I'm gonna call it a day. Yeah, Zoe. Do you want me to keep coding or do you have a question?
No, I have a question, but
Okay.
thank you. Thank you so much for the workshop. Could EBASE be applied to ex situ, such as lab experiments? If you were to set certain parameters like wind speed to 0 and par to constant, could you look at, instead of inter-site, like inter-experiment comparisons between differences in temperature? Or would you recommend against that?
The short answer is yes, you could. As long as the input data that you have satisfies what EBASE needs, it's going to fit a model.
Mhm.
Whether or not those results are bogus or not, I can't say. It would certainly be an interesting assessment. When we developed EBASE, we simulated data and used that to see if it recovered parameters that we knew were true. So we use synthetic data. I know you're not talking about strictly that. You're talking about experimental, where you could hold some things constant. I guess I don't see why not, why it wouldn't work. Just qualifying it with the fact that it's never been used on experimental
Mhm.
data. So,
Okay,
yeah.
thank you.
Stephen?
Yeah, I was just curious if taking a step up a level, maybe like, are you familiar with any examples of how net ecosystem metabolism has been used in a management context? Like, what are kind of the general, if there are examples that you're aware of, how insights from these types of analyses have been applied, I guess?
Yeah, that's a good question. I am not aware of any. Um, I want
Okay.
to emphasize what I said earlier about conventional metrics of ecosystem state versus metabolism. Nearly all regulatory standards for nutrients are based on nutrient concentrations or chlorophyll concentrations in estuaries. Um, that's simple, easily obtained, not fraught with assumptions like a lot of these, metabolic approaches are. So I think it would be difficult to apply something like this in a regulatory context.
Mhm.
I don't think it would be appropriate. What I do think it helps with is interpreting change and what could be driving it, and providing a more comprehensive assessment of ecosystem state. Like I said, those conventional indicators of trophic state, they're snapshots. And oftentimes regulatory assessments are just based on a few snapshots throughout a year. Um, so, we can debate, I guess, the merits of the assessment process, but in terms of how these estimates from EBASE or other metabolic models are used to supplement, I think they have potential, but I am not aware of any such applications. I wouldn't be opposed to it. Like the Piney Point stuff I was talking about, I've never seen a DO signal ever do that, and there are some pretty interesting changes in metabolism that followed as a result.
Mhm.
It helped me better understand the ecological changes, which could eventually translate to a policy change, or a reevaluation of the regulations. So it's more of an ad hoc thing rather than, um, yeah. I guess I'm going around in circles, but
Yeah, no, thank you.
yeah. Does that help or
So, I
further
mean,
confuse?
yeah, no, I think it does. Like in the context of Tampa Bay Estuary Program and stuff, it's like viewed as like another tool in the quiver, basically, for getting a just kind of taking the pulse of the area in a
Correct. Yeah. I
more
mean,
sensitive way.
it's an additional line of evidence for assessment that I think is much more comprehensive than conventional indicators. We are not using it that way, mostly because we don't have a good long-term record of continuous monitoring data in the Bay. That is being rectified somewhat. I think Amanda put a link in the chat to the Tampa Bay Observing Network. That's a relatively new program with a few stations around the Bay. I have not explored that information for estimating metabolism, but I would I intend to do so. Um, so these workshops are also part of an effort by myself to normalize NEM and assessments. So uphill battle.
Well, very cool. Thank you.
Yep. Well, any other comments, questions?
Marcus, I have a question. This is Amanda.
Yeah.
Since you mentioned T-Bon, one of the things we don't measure is PAR. What is the realistic way to, like, if there's that one site from USGS, in terms of like the spatial proximity of where these measurements are being made and using that for our sites throughout the Bay, what would your recommendations be for that?
Yeah, I don't think anybody's looked at that. Like, is it valid to use a station in Orlando or whatever
Okay.
to evaluate PAR in Tampa? I know that's a bit of a stretch, but like at the NERS, like the work that Jane Caffrey did, there's typically only one or two weather stations at each NER. And that information was, well, I might need to go back and look at Caffrey's paper, but I feel like that one weather station was applied to multiple sites within a reserve. And, that's the best you can do in a lot of cases. And I don't think that's necessarily insufficient for understanding what's going on with metabolism. Obviously, the best case scenario is if you have a co-located PAR sensor, but I know that's unrealistic. Personally, I have no issue using like for example the Tampa Bay data that I used early on. Um, I imported data from Lobo, that USGS station, and Port Manatee, which is fairly close but not co-located. And I don't have any issue combining data that are separated as long as it's not in a wildly different location that I'm expecting to be having different weather conditions. So I don't have a good answer other than it's been done that non-co-located places are often combined.
Yeah, I'm just thinking maybe we might need to look into that so we can do this type of analysis because it's
Yeah.
definitely worthwhile.
Yeah. I think the other approach, the ODM one that we have, doesn't use PAR, but it does require barometric pressure. It goes back to the model that's used to parameterize these things. But yeah, let's talk. I think there's opportunity to collect additional data to support something like this.
Okay, awesome. Thank you.
Yep. Yeah, Stephen. Did we lose Stephen?
Sorry, I was muted. In light of Amanda's comment there, I was wondering if you have any thoughts or plans in the works for, I guess, expanding this beyond like single station, like taking into consideration the sort of, the spatial uncertainties and stuff, and in
I
addition to
don't.
the temporal ones.
Most of these methods are station specific. I'm not aware of how that would even, I mean, in theory, you should be able to make assumptions about ecosystem state, but what does that really mean? It's really just the place that's being sampled. What area does that really describe? I don't think anybody really knows that. I mean, you can do actually this part of this project that generated this package was they did field work in Apalachicola where they set up a control volume experiment, which is basically a triangulated, triangle network of sensors to really look at where water is flowing in 3 dimensions or 3 dimensions.
Mhm.
And that does get at some of those questions, but I don't, beyond that, it's very site specific. I don't have any plans, at least furthering this work because it's not part of my main job. This was a project that I had started before I was at the estuary program, and it just sort of continued. I don't mind doing this type of work, but it's hard to justify if there's no funding, of course.
Yeah, understood.
But if this becomes something to be used, I'm fully there to support it, and I will continue to maintain the package. It's just a question of how much attention I place on it for additional development. So,
Great, thank you.
yep. All right. Well, I'm tired, so I'm gonna go. But definitely appreciate those who stuck around to the very end. I guess look for a survey in the next couple of days, as per the request at the beginning. Give us feedback on the tool. I know there were some things that I said I was going to include, that EBASE years function, the NEM, and the output. But anything beyond that, I'm happy to make this something that's more useful for you all. So just reach out to me and let me know. Yep, and you're welcome to everybody in the chat that's saying thank you. I always love to see that. But all right, I am going to close the meeting. We'll see you all next time.
Have a good one, Marcus. This was
Yep.
awesome.
No
Thank you
problem,
for
Ethan.
doing it.
Appreciate you jumping on.
Yeah, thanks a lot for doing it. See you later.
Yep.
All right.